brain, mind, and body symposium and workshop, so on cognitive neuroengineering for health and wellness. And so we have many participants here today. It's all online. It's great. So we'll start off with some welcomes and introductions from the sponsoring society. So let's get started. Yeah, Metin, please go ahead.
Okay. Good morning, good afternoon to everybody. I'm Metin Akay. I'm the president of IEEE Engineering, Medicine and Biology Society, also John Estan Foundation professor at the University of Houston Biomedical Engineering Department. I'm delighted to be here, and I would like to welcome to all of you on behalf of IEEE EMBS and also the organizing committee as one of the co-chairs of the workshop. And this is the second Brain, Mind, Body workshop sponsored by the IEEE EMBS and also co-sponsored by IEEE Brain, UC San Diego Institute for Neural Computation, and also Institute for Engineering and Medicine, Department of Bioengineering, as well as Qualcomm and Cowley Institute. There is, as we all know, there is an urgent need in the development of and use advanced technologies to monitor and control brain activities to treat neurological disease. And the approach is not on the systems level, but from the molecular all the way to behavior. These advanced technologies are indeed impacting our society, healthcare, and we would like to achieve this strategic goal, and we would like to build a very vibrant global ecosystems of engineering scientists and physicians, healthcare professionals, as well as industry leaders. And in this system, we openly exchange ideas, disseminate our research, and is indeed this ecosystem is the platform, which is the workshop. In 2015, Paul Sajda and myself and I discussed how we can start a unique workshop to brainstorm development of the advanced technologies for the brain health, actually. And our workshops, previous workshops, mainly focus on development of sensors, devices, computational methods for experimental and clinical probing. Also, we focus on novel, invasive, and the non-invasive approach to understand and also study the brain functions. And it was very successful. And in 2019, Gert, Shankar, Bruce Wheeler, and I had a lengthy discussion about how we can bring the diverse group of researchers and practitioners across academia, industry, and clinical profession to really focus on more futuristic integration of the unobstructive technology, neurotechnology, and medicine, and while focusing on minimally invasive neurotechnologies, and also the cognitive engineering, natural intelligence, and the translational engineering for health and wellness. I strongly believe that these workshops and this current workshop provide a very unique interactive platform to exchange ideas in the areas of brain, mind, and body initiatives, and with the leading experts, global experts, and also the academic, clinical, industrial professionals, as well as the students who are our features. I think this is a great opportunity. And I would like to single out one person who put so much time and energy on this workshop, Gert. Great to have you here. Thank you so much.
You're muted, Gert.
Yes, Shankar, please. Yes.
Good morning, everyone, and welcome to this second workshop. I'll be very, very brief. First, I want to welcome everyone, and I echo Metin in thanking Gert Covenbergs. We are very grateful to him, his immense effort in getting this workshop organized. A new feature of this workshop, the second workshop, will be the integration of scales across from the large scale, which is represented by a number of people here, including Teresa Szymanowski, and to the molecular scales and cellular scales, as illustrated by Rusty Gage in his presentation that's forthcoming. So we are really, I mean, the brain is the next frontier, but to understand the frontier, we need to really have the multiple scales that are well understood and portrayed. And of course, we had a workshop last year on grand challenges in biomedical engineering. And the brain was considered as one of the ultimately understanding the function of the brain and creating an avatar of the human brain. Ex vivo was considered to be one of the biggest challenges that's available. And with the eminent speakers who are here and researchers who are here, it is going to become a reality sooner than later. So I look forward to listening to all the wonderful talks, and welcome everyone. And let's please engage in active discussions towards this emergent new future, the fearless future of the brain era. So thank you again. Thanks and welcome. Thanks, Gert.
Thank you. So Paul?
Yeah, sure. So hi, everyone. I'm Paul Scheida. I'm actually the chair of the IEEE brain technical community. Here with Jack Gallant, who's the chair-elect, so he will be taking over in January. Just a little bit about the IEEE brain technical community, which started as an initiative, and we kind of got promoted into our own organization. The focus of the IEEE brain is to really integrate the activities in neurotechnology and neuroscience across the different organizational units and societies within IEEE, as well as serve as kind of a common interface to societies, academics, government organizations outside of IEEE. And so we work very closely with the International Brain Initiative. We're a member of that. We also work closely with NIH, NSF, and being thought leaders in terms of where new initiatives and funding can potentially be allocated. And activities like this, I want to really give a shout out to Gert also, because one of the things as IEEE Brain we've strived to do is really foster and help provide resources to activities that kind of transcend any given society or organizational unit, and truly look at new areas in which studying the brain might have major impact in health, wellness, and society. So once again, very happy to be here, excited to listen to the talks, and thanks very much.
Thanks, Paul. So Jack?
Jack, you're muted.
Sorry, I think Paul gave a good summary of the IEEE brain community and EMBS relationship to EMBS and the other societies. I just wanted to mention, at any given point in time, every area of science and engineering is limited either by theory or measurement. And right now, neuroscience is definitely limited by measurement, our ability to measure and manipulate things. And I think it's really fantastic that the EMBS is taking the lead on developing new instrumentation and devices, both to measure and intervene in the brain, because without a strong engineering society behind the development of neurotechnologies, the science isn't going to move forward. And I also want to thank Gert, because he has really been a Superman in organizing this conference. It's really been amazing to watch him.
Thanks, everyone. So this is, I will say a few words on behalf of the UC San Diego Institute of Neurocomputation, on behalf of Teresa Szymanowski, who has been director for 25 years of the Institute. I joined the Institute also about 12 years ago. So INC actually hosted the first symposium workshop 2 years ago. And so we plan to do this again in the future once we all return back to the real world, because after this pandemic here. Terry also was a keynote speaker in our first meeting in 2019, and he'll be also leading a panel, the IEEE Brain panel that will be tomorrow. So I would like to give a bit of a background of why we're doing this meeting after so many other neural engineering, neuroscience, cognitive engineering, and health, wellness workshops. So this is a very unique platform. So let us contrast the prevailing means if we're doing neurology or healthcare in general that is really driven by acute problems. When something goes wrong, intervene, and then you throw all your arsenal of techniques at it to solve or trying to solve that problem in a way when it's almost too late when something happened. And so in healthcare, that has become a success story, has been great. We have had all this beautiful successes, such as the brain stimulation, being able to really, say, solve Parkinson's, or at least remediate some of the symptoms of Parkinson's, and many other diseases, neurological, and I guess over the entire body. But so this is very intrusive and also expensive technology that is really, basically, you throw a sledgehammer almost at the body and the brain in order to solve some key problems. So this is also so we have gone very far in centralized care, right, where we all go to hospitals, so clinics when we're sick, and then for people that are far away from civilization, if you're not so lucky and you're far removed from a hospital, then you have much less chance to benefit from healthcare. So there's a need for a more just, global, and more effective and efficient healthcare that really engages the entire society, everyone. And also, it's a different way of doing healthcare. So rather than solving acute problems when they arise in very intrusive and localized fashion, why not be more preventive, taking care of health and wellness on a long time horizon with 24/7, health monitoring, or more generally, monitoring the synergies that naturally arise between brain, mind, and body, whether you're healthy or diseased, hopefully healthy, and then take advantage of the knowledge that you have there, along with technologies such as, we call this cognitive neuroengineering, right, or natural intelligence, basically understanding how the brain and the body work as a system together. And then coupled with that, some feedback strategies, closing the loop for doing new types of remedies, therapeutics. We can call them electroceuticals, but you can all more broadly, we call those unobtrusive technologies 24/7 that really can interact close loop with the brain and the body, where we put some smarts in those control loops. Basically, rather than fighting the body's natural functions or trying to surpass them, basically complement them, and basically taking advantage of synergies that naturally arise between brain, mind, and body for really promoting health and wellness. So that's a bigger picture. And so we already highlighted, let's say, in addition to this particular example of Parkinson's disease, unobtrusive remediation, more generally, we have this different pillars here of unobtrusive neurotechnologies, cognitive neuroengineering, and then closed loop therapeutics for clinical advances and health and wellness. So that's a setting. And so 2 years ago, under the great encouragement of Metin and Shankar, right, so we started this meeting. We decided to hold it at UCSD. Well, why UCSD? Because we had all this neuroscience and neuroengineering happening there. In fact, the Institute of Neurocomputation has been doing cognitive neuroengineering now for more than 25 years. So we had a great, so we called together the community, but a great meeting with about 150 attendees locally they actually came to the workshop, and we had students participate in posters and demonstrations. Basically, we were very enthused by the level of enthusiasm from the community, especially younger generations that entered the field and was really making an impact in showing unobtrusive technologies for health and wellness. Basically, this emphasizing the 3 pillars of neurotechnology, cognitive neuroengineering, and then translational health and wellness advances. So that was 2 years ago. Then came the pandemic in 2020 that put us all in a hiatus. But now here we're again. So now we're in 2021. The pandemic is still ongoing somewhat. And so now we're virtual. In a way, maybe we're partly lucky because we also discovered that virtual format is actually not exclusive or doesn't exclude active participation. And so today and tomorrow, we have this workshop and symposium happening entirely over Zoom. And we have about 700 people that have registered. Several are showing up today. Hopefully we'll have more participating soon. And we'll make this interactive. So in addition to having this mini symposia with invited speakers telling us about the latest advances in unobtrusive and minimally invasive neurotechnologies, and later today, cognitive neuroengineering and natural intelligence. Tomorrow, then translational neuroengineering for health and wellness, the 3 pillars of this symposium workshop. We also have then interactive posters during the lunch hour or the early lunch hour in California, late lunch hour on the East Coast, and probably a dinner time elsewhere or midnight as well as in the world. But so during the lunch break here, so we have this interactive poster presentations by students and other young researchers. We'll have the poster spotlights or highlights just before that, at the end of this plenary session, where we have all the presenters one by one giving us a 1 minute, just a 1 minute max overview of their posters. And then we'll have those presentations over Zoom breakout sessions. So everyone here at the workshop and the symposium is welcome to join and roam around in any of the breakout rooms where we have those 3 or 4 different themes of interactive poster presentations during the lunch hour. We have more demonstrations tomorrow. Basically, then those are live demonstrations of technologies, again, by young researchers and students. Tomorrow, we also have panels, interactive panels, engaging both panelists and the attendees. One is on transforming global health through innovation and sustainable technology, which will be led by Amy Cruz. And then we have a panel on melding mind and body in the age of the brain, led by Teresinovsky, basically highlighting the Brain Initiative at the international level, and particularly what IEEE Brain has been doing in this domain with different societies. And then we'll close and have the award presentations. In fact, so we have 14 poster presentations today, and tomorrow we have 5 demonstrations. Those were solicited from the community. So these were selected based on the great quality and the enthusiasm of the community. And so we're very delighted to have them. And so we'll select 2 best poster awards for student best poster awards, and also 2 student best demo awards for demonstrations tomorrow. We also have 2 awards that went to IEEE EMBS, EMBC, that will be presented here. So those were awards conferred by IEEE Brain, specifically for brain research, and this was for the EMBS Society. And that'll be it for the workshop and the symposium. So we look very much forward to have you here, and so please interact. You're welcome to interact not passively, but actively. And so we set up this Zoom interface where participants can just chime in and speak up. We sent you a note about etiquette, Zoom etiquette. So please, for the participants, so please only unmute yourself if you're given. So basically, you raise your hand if you want to talk, raise your virtual hand if you want to talk, and then unmute yourself and then you speak up. And you can also show your video if you like. That's all up to you. Now the breakout sessions are all free form. You can just go there and talk and present. Even you can show your screen if you like. So that's all free form. And so if you have any questions about the format, so let us know. We're happy to help you through, and we'll make this a very interactive workshop. So with that, let's get started with the first mini symposium. And so in fact, for the first mini symposium on unobtrusive and minimally invasive neurotechnology, we're delighted. So we have Ricky Miller join us here as co-chair of this symposium. In fact, Ricky, who is at UC Berkeley, she was our very first speaker of the very first Brain, Mind, and Body Symposium workshop in 2019. In fact, she gave it, she took off with a really great start with her talk on unobtrusive and minimally invasive technologies. And so today we're very excited to have the following talks. So we'll have first, so we'll have Professor Milin Zhang of Tsinghua University in Beijing, China, give the very first talk. This will be on circuit design for low power neural interface implants. And so the focus here of the session is this interface between machines and brain and body together, right? Specifically, they're using those new technologies that can do this very effectively and very efficiently. So Milin has been at Tsinghua for several years. She's there in the faculty. Before she got a PhD degree from University of Pennsylvania. In fact, there she did some great work on the one of the first large-scale brain computer interfaces developed there. So with that, let's give it a start. So Milin, so please, I'll let you share your screen.
Sure. Okay, let me share my screen first. Thanks, Gary, for the invitation, and thank you for the introduction. It's my great pleasure to join this symposium, although that I cannot physically join you all, and I believe that it's going to be a great poster session, which I can hardly join later. But anyway, it will be my great pleasure to share some of our recent research. And so today I would like to talk about some of our circuit designs for the topic of low power neural interface implants. So excuse me, that's because I want to save some internet and I do better turn off my video. Otherwise there will be some very bad connections according to my previous experience. Okay, so today I will gonna really talk about from the circuit point of view that how to design a low power neural interface. So what is the concerns, and so from the circuit point of view, what is very important. Excuse me, why my slides doesn't. Let me restart my slides since it's full. That works.
That's perfect. We see it. Perfect.
Yes, but yeah, yes, it's just oh here. Okay, this works finally. So I will first briefly introduce that some understanding of what the neural interface looks like from the point of view of circuit designers, and also the challenge and possible solutions that the circuit designers have provided. And so finally, I will conclude my talk. So in fact, that when we talk about neural interface, that's why we want to do it. So this is fully bio-expert concept. When we talk about neural interface, we first look at ourselves for human beings. That there are neural loop inside of our body. We have the motion pathway, which transfers the information from the brain to the entire body. And also we have the sensory pathway, which transfers all the activities and feelings and the subtle sensory information from the body back to the brain. This is how the human being works. And so when we talk about neural interface, is that the engineers want to mimic what the human being naturally did it. We want to build an artificial pathway between the brain and other man-made devices. So in order to do this, so we try to do exactly what the brain communicates to the body. So the brain has the motion pathway. The motion pathway can read information from the brain. So okay, let's also build a reading pathway. In the reading pathway, we first acquire signals from the brain, and we translate it and decode it into feature extractions. And those feature extractions will further turned into different control comments. And those control comments will be either sent to man-made devices, for example, the PC or the machines, or sometimes even we can directly send it to other part of our body, for example, to send it to the hand, to the leg, and to control it. And so this is the reading pathway. We mimic what the motion pathway did. And then we also want to send information from the man-made devices, from the environment, or from the other part of the body back to the brain. In order to do this, we must first to collect the information. Those informations may directly come from the environment. For example, what's the temperature of the room, and what's the humidity of the room. And also we can collect the information from the PC, from the computer. And we collect all those information and encode it into different modulation waveforms. And those waveforms will be further turned into pulse outputs in current or in voltage mode. And those current or voltage pulses will be sent into the brain. And that's how the brain received those informations from the outside of the body, from man-made devices. And now, by doing this, we have two artificial pathways. One is from the brain to the outside of the body to the outside the man-made devices. And the other is from the outside of the body, from the man-made devices back to the brain. And this turns into a closed loop. So such a neural interface is a very important technology for frontier brain studies. By implementing such a neural interface in clinical practice, doctors can use it to explore new ways to cure Parkinson's diseases. For example, Medtronic has proposed and have their product for deep brain stimulation. And by turning on the deep brain stimulation, it can obviously change the activities of Parkinson's patients. And also from frontier researchers, we use such neural interface to help people to regain some abilities. For example, Brown did the research on directly read information from the brain to control the robotic arms. And also recently, in Cell that we can read the papers talking about that, how we can translate the information from the vision contact into the letters, and then we can the vision. And this is really great. But when the circuit people look at this, the first question is how to really realize such as good systems in circuit. So here shows the block diagram of a neural interface. And so there are two ends. One is the brain, the other is the man-made device. So we need to establish a two-direction pathway between the brain and the man-made device. So we call it a neural interface. In fact, I like the word interface very much. Interface is to connect two ends. And we further divided it into 4 parts. The first part is that we implemented a tissue interface. A tissue interface is try to translate the biochemistry signals into either voltage or current. As we all know, voltage and the current signals are very friendly to circuit. And once the signal is already voltage or current, we can easily manipulate it in circuit. And now here comes the second part, the sensor interface. The sensor interface can do 2 things. One, it can amplify the original signals acquired from the brain and to digitize it and to do on-chip signal processing. The other way is that to directly the other direction, it can receive the signals from the outside of the body, from the man-made devices, and then generate the different patterns and translate those patterns into voltage or current pulses and send the pulses into the brain. So this is the sensor interface. And we also need a third part, the air interface. An air interface is wirelessly connected the in-body part and the out-body part. And also signal processing is important. So here is the more complicated and high power hungry signal processing we need. And it's usually performed off the body. And for such a big systems, but when we design it, there are a lot of different challenges. And today that I will mainly focusing on one path, the reading path from the brain to the man-made device, and focusing on the challenges in this pathway. For this pathway, the first challenge is that we always want to acquire as more information as possible. And in recently, we can see papers and the news that saying that there are already thousands of channels or even tens of thousands of channels available in different systems. And while the total number of channels keep increasing, there is a heavier and heavier workload for the analog front end. For the analog front end, we need to first amplify the signals. So if there are only 10 channels, that is won't be a big problem. But once there are thousands or even tens of thousands of channels, that's the power consumption of the analog front end will be a very, very big problem. So for such implant systems. So because for implant systems, we do not have a very big battery. So the power budget is very, very limited. So how to solve these problems? So in fact, there are already some ideas and solutions have been widely used. So first is that because there are more and more and more channels used and integrated in the systems, we stopped implement an amplifier and ATC for each channel. Look at the very left figure. So this is what we did at the very beginning. At the very beginning, once we only have several channels, we can implement it one amplifier and one ADC for each of the channel. And we put one digital mixer at the end. And that means we just convert the parallel output from the ADCs into a server or output. So this is a very straightforward solution. So the problem is that usually the air consumption is very high because of the ADC in each of the channels, and the power consumption is usually also very high. But of course, the advantage is that we can easily manipulate channels by channels. So one very straightforward improvement to save area and power consumption, that how about for all of those channels, we share the amplifier and the ADC. So we put an analog mixer between the electrodes and the amplifier. So this is a very straightforward solution. And so it seems that works perfectly because we only need one side of the analog send end. But there is a problem because from circuit solutions, that if we want to implement an analog mixer, so usually we use switches a lot. And for those switch structures, that the impedance is usually relatively low. And so this is very unfriendly. We need high impedance, high input impedance for a good signal quality acquisition. So in fact, the most commonly and widely applied solution for the time multiplexing recording schemes is the third one, the very in the very right figure. So here, the first for each of the channels, we implemented one amplifier, and then we inserted a mixer between the amplifier output and the ADC. So that means the ADC is shared by different channels, but not the amplifier. By doing this, we can control the impedance by well-designed the amplifier. And the amplifier can enable a very good noise performance as well. So now it seems that we already solved the very first problem. So while the channel numbers increases, that we do not need to set up one set of amplifier and ADC for each of the channels, but we share the ADCs to save some power consumptions and to save some silicon area. So, but there is more problems. So the second problem is that let's look at of the signals we are trying to acquire. That is going to be the task for the amplifier. So if we check the brain, and we'll see that vertically the brain consists of multi-layers, and for different signals can be acquired from different layers. For example, if we go to the deep brain, we will achieve the action potentials, the specs we are looking for, and also local field potentials. For action potentials, the band of interest is usually in several kilohertz, and the amplitude is about a millivolt. And the local field potential is a little lower. Both the frequency band and the amplitude is usually around several hundred hertz and with the amplitude of less than millivolt. And if we go to around the school or even outside of the school, we're gonna achieve ECOG and EEG signals. And those signals located in the range are typically like lower than 100 hertz, and the amplitude is even lower. It's going to be as low as several microvolts. So here we put all the signals that we can acquire in this one figure. And you can see that there are some white lines. And those white lines are the noise interference in this band. And you can see that those noises are very strong and almost everywhere. So that means we are trying to acquire some very small signals, but the small signals are buried in very strong noise. How to do that? There are some solutions. So for example, if you just simply want to go to Radio Shack and to just purchase them off the shelf IC chips and to make up your own system, that you can just go to the TI chips, and they are very good low noise amplifiers with ADC integrated in one socket. And I think that this is one of the simplest solutions if you want to acquire some EEG signals or even action potentials. So the input noise performance is really good for those off-the-shelf chips. But I think that one of the big issues is that the power consumption is really very high. It's usually around millivolt for each channel. And if you want to integrate it really a lot of channels, I won't suggest you to choose this solution. So alternative solution is has been proposed by Harrison in 2003. So Harrison proposed to implement a pseudo resistor-based amplifier, and so this is a very good design, I would like to say. So it features a very good area efficiency and very good power consumption, and but there is still some problems for Harrison's solution. So first, that this structure can hardly achieve a very good input reference noise below 1 microvolt. So because of the flicker noise, so that means that if you want to acquire equal EEG signals, this is may not a good solution. And also because the use of the pseudo resistor is very sensitive to the PVT, the process voltage and temperature. And also that the THD is now very good. So because of the pseudo resistor. And another solution is to use chopper structure. And chopper amplifier, in fact, it's one of the popular solution and widely used solution for neural signal processing. And so the key advantage of chopper amplifiers, it features a very low noise, and the flicker noise is because the flicker noise is filtered by the chopper, so the input reference noise usually can be as low as less than 1 microvolt, and also that the CMR is good, and but the problem is that usually there is the good large ripple, and the input impedance is not very good. So we also want to find out some even better solutions. So we try to begin from the chopper. So we try to improve the performance of a chopper and to design even better ones and more suitable for neural signal acquisition. So as I mentioned that there are 3 key problems for chopper, or 3 key disadvantage of chopper. Is first that the ripple is not good, and there is DC offset, and thirdly that the input impedance is relatively high. So we try to find a solution to solve these 3 problems. So first for the ripple, where does the ripple come from? So in fact, that's for a chopper amplifier, the ripple is generated by the offside of the first stage, as you can see here. That the offside current will flow through the first stage, and it will be modulated by the chopper switch, and then the current will be fed into the second stage, and then that generate a large ripple at the output. So in order to solve this problem, we propose a very straightforward solution. That we insert a pair of capacitors to cut off the propagation pathway of the ripple. And so because we cut off the pathway, that we add a feedback loop to improve the stability of the first stage. So by doing this, we reduce the ripple from at the output, but at the same time that we didn't ruin the stability of the first stage. The second problem is the DC offset. So if the DC offset originates from the electronic tissue interface. we may use different electrodes for different tasks in brain studies. And so here you can see on the left, this is the model, a circuit model of the electrode tissue interface. And that means that when we design it from a circuit point of view, that we can simply use this very simple model to do simulation. And so you can see here, so the impedance of this interface is very large. And so because this impedance is very large, so if we want to effectively acquire the neural signals, we need an even larger input impedance for our circuit. And as you can see here, that according to simulation, that the DC offset of such electric tissue interface can be as high as to sometimes even 50 millivolts. So in fact, this is really a disaster to an amplifier design, and this can easily saturate the entire amplifier. So we definitely have to solve these problems. So in fact, that from in circuit, that if we want to solve the DC server loop, DC offsite, one typical solution is that we can use DC server loop. And as you can see here, but there's a problem that previously that I have shown you that what's the band of interest of our target signals. So our target signals varies from less than 1 Hertz to several kilohertz. So that means if we use DC server loops here to solve the DC offset, we need a very low high pass filter point. It will be less than 1 Hertz. And so that means we need to integrate a very large capacitors, the CHP in the high pass. So as you know that for circuits, we implemented a very large capacitors on chip. This is gonna occupy really a lot of silicon area, and this is very unfriendly. So we must think about another way to realize the DC server loop. So we proposed a new DC server loop based on the GMC integrator to cancel such a offset. So first that we put resistive divider before the integrator to enhance the linear range. And also that for the high pass corner lower than 1 Hertz, that we need very lower transconductance of the OTA. And so compared to the traditional structures, that this design definitely improves the noise performance and the PVT sensitivities. And for the offset cancellation range, that the offset cancellation range is still determined by the CHP. And so the input impedance C in can be set to several picofarad, and the voltage we use here is 1.8 volts. And so for this structure, that we only need about several hundred, in fact even less than 200 femtofarad, and the high pass frequency can be calculated as shown here. And the alpha is the voltage divider, the division factor, as the voltage divider is on the very right. And so this is the factor of the voltage division. And so in this design, that we set it to 0.8, and we design the very low transconductance OTA to the transconductance of it to be 45 picos F. And so after we designed such a systems, we need only we can achieve a high pass of corner at around 0.4 Hertz. So this is exactly what we want. We need a less than 1 Hertz high pass corner. And the third problem is the input impedance. In fact, this problem originates from the chopper structure. And for chopper structures, that as shown here, that you can see there are switches. And because the use of switches, usually that the equivalent impedance is relatively low. For example, in our design that we use a chopper clock of 20 kilohertz, and the equivalent input impedance is only about 5 mega ohm, and this is really low and far from enough. So in order to improve these problems, that typical solutions is that we can introduce feedback loop. But the problem is that the upper feedback loop can now solve the problems that cannot improve the impedance when it's under around 100 hertz. So in order to further improve the input impedance around the very low frequency band, that we add another feedback loop, the lower one, and by at this part, this feedback loop, so we introduced the DC signals from the DC server loop. You remember previously that we add this DC server loop to solve the DC offside problems. And so here, there are DC informations, and we can just introduce the different informations from the DC server loop and feed it back to the input. So that means that there will be less current required from the input node to realize the high input impedance. The fabricated our chip and compared to what we mentioned the previous solutions, and same as solution 2 and 3 as the pseudo resistor ones and the traditional chopper ones, that it also features the a microvolt, around microvolts low power consumption, and the noise performance is 0.65 in the low frequency band and the 2.40 in the high frequency band. And in fact, that for the high pass corner, that we made it configurable, and it's configured. It can be configured from 0.35 hertz to 54.5 hertz. So for the reading pathway, in addition to what we just mentioned, the challenge from the amplifier, there is also challenges from the air interface. So because this is a scenario that we plan to implant the device into the body, and that means that we need a solution to wirelessly communicate between the inside of the body and the outside of the body. And so as we all know that radio frequency transmitters is very power hungry. So how can we effectively transmit these informations from the inside of the body to the outside? So if we check the state-of-the-art transmitter designs, one of the most popular and the most mature commercial solutions, the low power Bluetooth, it's worked around the 2.4 gigahertz, and it's usually that the state-of-the-art Bluetooth transmitters consumes about several millivolts for megabit per second data throughput at 0 dBm output. And for those transmitter, usually that the most power hungry part is the local oscillator and the power amplifier. So if we want to reduce the total power, that we must put our focus on these two parts. And so in fact that if we put the circuit inside of the body, we cannot transmit data at 0 dBm. This is not safe for the body. Usually we need a little lower, usually for example, the minus 10 dBm for the output power of the PA. And so in fact that if you use the Bluetooth, you can just directly change it by changing the input current. And I will discuss a little later. That won't be a good solution. Let's first look at the architecture of the transmitter itself. So we need to choose the big architecture first. So there are different solutions. So for example, the very classical IQ transmitter for cognitive motivation. This is widely used in a lot of transmitter demands. And there is an IQ mixer, as you see, and a PL-based 19-degree hybrid with the local oscillator and connected to RFPA. And so this structure is really used a lot. But in fact, that for ultra low power transmitter designs, this is not that popular. In ultra low power designs, that power transmitter is applied more than the traditional IQ transmitter. And so in a power transmitter, it converts the IT and QT into an amplitude, both of the IT and QT into an amplitude signal. And the modulation is achieved by tuning the output of the power amplifier according to different phase generated from the PLL. And in fact, this structure can be further simplified by totally remove the amplitude path. So that means that only the phase modulation is saved. This structure is the most popular ones for ultra low power applications, for example, low power Bluetooth and GSM. And we also use such a structure. So as I just mentioned, that from the input inside of body to the outside, we cannot directly send out 0 dBm. So we need to reduce the output power. And so for those ultra low power transmitter designs, usually that switch mode PAs used a lot. For example, as shown here, that the class D PA or class EF PA, those PAs are very good solutions because that those kind of switch mode PAs can features a very, very high drain efficiency. So theoretically, it can be as high as 100%. So the problem is that, for example, you can see here that for the class D, that we need to drive 2 transistors in the input, and for the class EF, that also that there are 2 transistors need to be driven, and so if we want to reduce the output power of the PA from 0 dBm to lower than 0 dBm, so we can just simply reduce the driving current of the input switch. But there's a problem. If we reduce the driving current of the input switch, that it will result in increasing of the turn-on impedance of the switch. And so that means that the PA efficiency will be sacrificed if we reduce the output. So that's definitely it's not what we want. What we want is that we want, even that we change the output power, that we still can keep a relatively stable or high efficiency. That's our goal. So let's see that how to realize this. So we use a single-ended class E PA. So for single-ended, as shown here, that there is only a single switch need to be driven. So that means that definitely the lower power consumption can be expected. And so here, as you can see, that we have the class E PA, and the switch is controlled by the signal weight control. And so the duty cycle of the weight control is D, we define here. And so we can do some derivation. And so we can calculate the switch voltage Vs through the CS, the LVDD, and the IRL. So previously I mentioned that theoretically 100 efficiency can be achieved. So when 100% efficiency can be achieved, so only if that we meet the 0 voltage switching condition and the 0 voltage slope switching condition. If we meet these 2 conditions, then theoretically 100% efficiency can be achieved. So we take the Vs into these 2 conditions, and then that we can get the solution for phi as shown in the bottom. And so you can see from this equation that phi is definitely relatively to the value of the duty cycle D. And here I plotted the relationship. And you can see that here, this is on the x-axis, this is duty cycle, and what is the y-axis? The y-axis is Kp, and the Kp is relatively to the output power. The output power is equal to Kp times VDD squared over RL. And so we can see from the numerical plotting, and the Kp is proportionally to D. So that means that we can tune the output power of such a class EPA just by changing the duty cycle of the switch control signal we control. And in addition, in order to meet, previously we mentioned, we need to meet the 0 voltage switching and the 0 voltage slope switching conditions. So in order to meet these two conditions, the input equivalent reactive X in and the CS are also tuned with the changing of the duty cycle as shown in these two equations. So we define KL as the X in over R in, and so this is a ratio between X in and R in, and we can calculate CS according to KS. And we also plotted together with the previously we plotted KP, and here the yellow line is the KC and the white line is KP, and from it's KL. And from this plotting we can see that when we use a lower duty cycle to realize a lower output power, we need a large X in. So how to really realize the duty cycle control X in? So we need to control X in according to duty cycle. And so in order to do this, we added the on-chip transformer-based matching network. And so because we want to save the total volume size of the system, so that we integrated the fully on chip. So that means the Q factor of this fully on chip integrated transformer is not very good. It's relatively low, and so the loss of the transformer will reduce the overall efficiency. That's what we expected. So in order to solve these problems, in order to solve these problems, we well designed this. We well designed of the Cs of L based near the optimal efficiency. And as you can see on the left plotting, and it shows that the x-axis is the Cs of L, and the y-axis is the matching network efficiency. And so according to this, that if the peak, we can find the optimized L value at the peak, that if it is about, for example, 20% higher or lower from its peak, that we can see that the efficiency, the y-axis drops only about 0.5%. And that's exactly what we want. We want the circuit robust enough to the changes of the output, to the changes of the output to the changes of the output power of the PA. So that's exactly what we are looking for. And the third problem is that for the single-ended class EPA, that the harmonic distortion is always a problem. So in order to solve these problems, that we added the pair of the parallel resonator, the LH2CH2, to reduce the second order harmonic, and we use the CH3 to reduce the third order harmonic. And as you can see on the left, that even that for such a PA, that if we check the voltage transfer function from the input to the output, from the VS to the V out, that there are two zeros. And so as you also see here on the left, so there is a very deep valley at the omega 0. And so from the numerical analysis, we can see that there is 37 dB reductance of the second order harmonic and a 7 dB reductance at F0. And per se, I earlier mentioned that we can optimize the number of the CF to realize the omega z of 3 times of the omega 0. And by doing this, that this matching network and features shown here for the third order harmonic, that is about 22 dB suppression. And so finally here shows the block diagram of the entire transmitter, and it includes the proposed single-ended class E PA. And so the original baseband data from the very bottom left corner is fed from the SPI, and is encoded and modulated before it's being sent into the shaping filter. And the shaping filter generates the frequency control word. And so the baseband signal is generated based on IEEE 802.15.6. And as you can see here, that the frequency control word is the input of the PLL for phase modulation. And the audio PLL performs both the channel and the phase selections, and also the phase modulation. And so the PA is tunable according to the duty cycle, as shown here, the duty cycle control word. And so we also used an on-chip matching network, as I mentioned earlier. And so it's a fully on-chip to solve the harmonic, to realize the harmonic suppression. And this is fabricated and tested. And from the testing, we can see that the total power consumption of our transmitter at with a 0 dBm output is only 4.85 millivolt. And when we reduce the output to -3 dBm, the total power is 3.22. And when we reduce it to -10 dBm, that's the output power is 2 millivolt. And so the power consumption, I already mentioned that the most power hungry part is the local oscillator and the PA driver. That for these two parts, the power consumption for the local oscillator is around 300 microvolt, and the PA for the PA driver is less than 300 microvolt. And the measured FSK error of the circuit with a M of 2 is only 2.3%, and for M of 4 is 1.57%. So I think it's almost time, and let me quickly summarize that. So today that I shared you some of the design concerns for the reading path. And for the reading path, while the total number of channels increases, that there is a big workload for the analog front end. And so time multiplexing sharing schemes have been widely used, but we still need to improve the performance of the amplifier itself. And also that for the reading path, another key issue is that how to reduce the power, or how to improve the power efficiency for the transmitter to well connect the inside of the body part and the outside of the body part. So if we check the trend, that we can see that for the neural interface, that we are trying to, from the circuit point of view, we are trying to push the energy efficiency and the voltage volume efficiency of such a system. So we are trying to use less power and less volume size to realize more functionality, and for the frontier brain studies and also clinical exploration. And so in order to do this, there's still way for the good test events and the system solutions. And so I think it's really a big topic, and far from here for such a short time to finish. And so I think this is just a start. And so hopefully we can have some other opportunities to share more discussions on this very interesting topic. Okay, this is the end of my talk. Thank you.
Thank you, Milin. And so we give you a warm applause over Zoom. So a question. So I know there are some questions on the over the chat window. In fact, there's one hand raised. So again, anyone who would like to speak up is welcome to do so during the question and answer sessions. And so I see one, yes. So please go ahead and ask a question.
Hi, this is Dr. Raut from Concordia University, Canada. Do you hear me?
Oh, yes,
Perfect.
I can hear you.
Oh, thank
Hi.
you. Yeah, I'm just curious to know, in case you or anybody like your associates or in that area thought of processing the signals as current, because mostly I find that you are using non-techniques or not building blocks, using voltage mode processing, and you have improved upon those modules. But is there a possibility to either work in current mode, which can lower the voltage, lower the power, but at the same time, current and voltage cannot be entirely separated. So there may be a mixture of current mode processing and voltage mode processing. So did you consider applying current mode signal processing in the near future?
Well, so for myself, that's for the very near future, for example, for my next tape out and maybe the tape out for the coming year, I haven't had the plan to try current mode yet. And so recently that, yes, power consumption is really a big issue. And so I think that you imagine the scenario that when the voltage level is really, really low. And I think that for my very recent and very near future coming scenarios, that what I face is mainly for the signals inside of the brain. And in fact, that is relatively not that low at least compared to EEG, for example. It's relatively high. And so at least for myself, I didn't try this method yet.
Thank you.
So I have a quick question, Milin. So you showed in your power amplifier, you showed a mutual inductance, so a transformer. And so what I can know is, did you include that on the chip? And if so, what quality factor were you able to accomplish, and how does it affect the performance?
So yes, that's as I mentioned, that because it's a fully on chip, that we cannot expect a very high Q factors, and so that yes, that's always a problem.
Thank you. Any more questions? And we can have more questions. Oh yes, there's a question. Yes, please feel free to raise your voice now. Yes, I see a second hand. Please go ahead, and you can just introduce just your name if you like, so we can all know who you are. Thank you.
Hi, so my name is Umnia Mohammed, and I need to start with thank you so much for this entire process. It's really helpful for those who are freshers. I have a doubt for those who are, a newcomer, a new beginning, and they're very deeply interested like me. Where would be the starting point to enhance their journey in order to acquire so much more in-depth information? So where would you prefer, advise someone who's a newcomer that where they should actually start from, in terms of research, in terms of experiments?
Excuse me, there are noises. Can you repeat? Sorry, excuse me.
Hi, can you hear me better?
Yes, that's better.
Okay, thank you so much. I would like to say thank you so much for all this entire opportunity. It has really helped open up many doors of knowledge and understanding for many newcomers like me who are very deeply interested in this field and are pursuing medical engineering as their education level. Where would you suggest someone to start their research from to acquire more and more knowledge and information as they go along the way? And for someone who's really interested in such field. So where would you see as a starting point?
This is really a very, very good question. And in fact, that's I also looking for a good solution and the answer to these questions, because every year that when I have a new PhD student in my group, I always think about, yes, which class he or she should take at the first year, and what's the fundamental knowledge that he or she need to first learn from classes, from course, from books. I think this is always a good question, and because this is a topic not only about circuit, not only about biomedical. I think that yes, we do need to take different classes from neuroscience, from circuit, from signal and systems, from even material science. I think that's what we for people that's interested in this part, we really need to read more and learn more classes. And for myself, that's at the very beginning, almost more than 10 years ago, when I first entered this research area, I have almost no idea about biomedical and neuroscience and pure circuit and the system person. And it's really takes me quite a long time to finally understand what my colleague from neuroscience talking about. And I think that myself is in the department of EE, and I think, for example, Gert is in the department of biomedical. I think biomedical engineering is most friendly to such a research area, especially even for my students, I would sometimes suggest them to take some courses from bioengineering, because biomedical engineering perfectly combines biomedical and engineering. Not too biomedical, that is because that's if there's a lot of very biomedical languages and talkings, it will be really hard for engineering students to get started. But biomedical courses usually make a perfect combination between these two. So I would suggest you to begin from pure biomedical engineering courses. And once, for example, for some of you are more interested in circuit, you can take more pure circuit courses to get deeper. But if, for example, if you are more interested in some topics of the biomedical part, you can take more biomedical courses to take it deeper. I think that may helps you or make it a little easier at the very beginning for the newcomers.
Let me also make a pitch here to so there is a so the solid state circuits society at the International solid state circuits conference organizes several tutorials, and there have been tutorials on biomedical circuit systems. In fact, Ricky gave a beautiful tutorial just last year, and so you're very much encouraged to check out those tutorials. They're very helpful for someone who wants to get started in the field. So this brings us at the end of this the first half of the session. We have, in principle, a quick break, although actually the break is almost over by the clock, but we can still have a 5-minute break or so before we convene with the rest of the session. So thanks again, Milin, for a great talk. And so now we have we can also try out the breakout rooms. In fact, we'll open all of them now. So we have 4 breakout rooms, and those 4 breakout rooms are aligned with the 4 poster presentation that we have during lunch hour, not now, but later. So you can already start roaming around the next 5 minutes or so, right? Before we reconvene with the session, if you want to try things out. Just one suggestion: if you can't seem to roam around and go to a breakout room of your choice, it probably means that you need to update your latest version of Zoom 5.3 or later. So that will let you then roam around, and that'll be important not now but later, I guess, for the poster session, interactive poster session. So with that, we have a quick break. So we'll be back by 9:25 Pacific time, and so you figure out where it is around the globe. Thank you.
Hi, everyone. Welcome back. Can you hear me okay?
Yeah.
Great.
Yes.
Wonderful. Thank you. It's my great pleasure to introduce Professor Duygu Kuzum. She's an associate professor of electrical and computer engineering at UC San Diego. She received her bachelor's degree at Bilkent University, her PhD at Stanford University, and was a postdoc at the University of Pennsylvania. Her research focuses on applying innovations in nanoelectronics to develop new technologies which will help better understand circuit level computation in the brain. Earlier this year, her group published a very nice Nature Neuroscience cover article on a flexible, transparent implant that monitors communication between multiple brain regions at once. She's won many awards. Recently, she received the NIH Director's New Innovator Award, the NIH NIBIB Trailblazer Award, the IEEE Nanotechnology Council Young Investigator Award, and I could go on, but let me instead introduce her and let her tell you about her group's research.
Okay, thank you so much for the introduction. It's a pleasure to participate in this mini symposium and share my research with you and learn about other ongoing activities in the field. Can you hear me well? Looks like okay, nobody complained, so I can go ahead. So today I'd like to tell you a little bit about some of the ongoing projects in my lab related to multimodal neural interfaces for probing brain circuits. So I like to start my talk by reviewing our neurotechnology toolbox. So if our goal is in general is to understand the information processing in neural circuits, we really need to record neural activity with high spatial resolution, high temporal resolution, and cell type selectivity. So in our toolbox, there are different tools offering different advantages. So the first one is electrophysiology, of course. Many of us use it. It's widely used in basic neuroscience research and medical applications as well. Electrophysiology is a great technique. It provides very high temporal resolution, but the spatial resolution is limited, mainly due to 3D inaccessibility of the brain. Even we use the most state-of-the-art high-density neural probes, we are still trying to sample neural activity that is generated by a 3D volume by using a 1D probe. So on the other hand, in the last 2 decades, optical techniques such as multiphoton microscopy, they basically provided us new opportunities to image from large populations of neurons simultaneously with spatial, cellular level spatial resolution, as you see in this movie recorded by my lab. So optical imaging techniques are great, but their temporal resolution is limited, mainly due to slow kinetics of indicators and low frame acquisition rates of microscopy setups. And finally, optogenetics have been widely adopted in neuroscience research because it provides very selective and fast control of neural activity, which is a great tool that is widely used to study connectivity, causality, and neural circuits. So towards our goal of understanding like information processing neural dynamics in the brain, it seems to make sense to combine different advantages of these techniques, high temporal resolution, high spatial resolution, and selectivity in multimodal experiments to be able to achieve our goal. Multimodal experiments are not only desirable for high spatial resolution, spatial temporal resolution, and selectivity purposes, but they are also important to bridge the gap between clinical research, which mainly relies on electrical recording, electrophysiology, versus basic neuroscience research, which utilizes new transgenic animal models, optical techniques that are not necessarily human compatible. And in addition to that, these multimodal experiments can also be used to provide the ground truth information for cell type identification when we use different machine learning techniques along with our recording experiments. So multimodal experiments, in summary, I try to give this general message of they are very important, but they're also at the same time difficult to achieve with existing neural probe technologies. And the reason for that is most of the microelectrode technologies are made of opaque materials such as silicon or metal. And since these materials are opaque, they are not compatible with multimodal experiments that utilize optical techniques. Because they're opaque, they block the field of view, they generate optical shadows, And since they absorb light, they also produce light-induced artifacts, which can severely interfere with neural recordings, and they are difficult to deal with, especially when we decide to perform like closed-loop applications. So to address that problem, in my lab, we are developing optically transparent neural electrode arrays based on graphene. So this movie is 3D reconstruction of brain tissue, including neurons and blood vessels that are directly imaged through a transparent graphene array implanted over cortical surface, which is shown with false green color in this movie. So using this transparent graphene arrays, we can actually seamlessly integrate electrophysiological recordings with optical imaging and optogenetic stimulation. So today I'll tell you some examples of graphene-based neural interfaces and their uses for multimodal recordings in different experimental settings. Then I will actually, in the second part of my talk, I will introduce you a new paradigm which we call virtual recording of neural activity, which makes use of cross-modality inference using multimodal recordings in different experimental settings. And in the last part, I will introduce this new probe technology, neurofilm technology, that we employed to a specific problem to understand neural activity related to memory and learning in the brain. So let's start with the first part. So graphene is a material that is actually used for many other applications in the area of semiconductors or devices. However, what are the advantages of graphene for neural recordings or implantable neural systems? So the first one I already mentioned, so transparency of graphene, it's an optically transparent conductor, so it allows us to simultaneously record an image from the same set of neurons. So that is a very unique property which already makes it very desirable for multimodal settings. The second property is artifact-free. So because graphene does not generate any light-induced artifacts, so we can actually seamlessly integrate electrical recordings, optical imaging, optogenetic stimulation, or any other optical modality without any crosstalk in the same experiment. So graphene is actually, as shown in the schematic, it's a monolayer thick material. So it's the hexagonal lattice of carbon atoms. It's extremely flexible. So the flexibility of graphene is important for building neural implants that are conformal with the brain's curvature and provides good mechanical coupling with the tissue. Finally, graphene also blocks diffusion through it, so it can actually serve as a protecting layer that prevents corrosions to protect the underlying materials in implantable medical devices. So graphene, you may think that it sounds like an exotic material, it's one atomic layer thick, but it's actually have been used already in many commercial applications, including additives, biosensors, and as a transparent conductor in smartphone screens. And more recently, there are also graphene foundry services offered by a company called Graphenea. So it's now possible to grow graphene in the wafer scale and actually fabricate some graphene-based devices in the graphene foundry for various applications ranging from bioelectronics, chemical sensors, photodetectors, which is a great opportunity in the context of neural implants as well. So how do we build these graphene devices? So this is just a very simple fabrication flow, but it could be modified depending on the particular design. So we first start with like a flexible polymer film, which is also optically transparent, deposit metals, pattern them, and then that is followed by a graphene transfer step, which we use chemical wet delamination of graphene for the graphene transfer. And then we pattern it and deposit the encapsulation. So because graphene is a monolayer thick material, transfer step is extremely important. So during the transfer, it really needs to be taken care of that no cracks are formed on the graphene surface, because that could result in array failure. And another step is basically the cleaning. Because graphene is very sensitive to residues or contamination, it's very important to perform like extensive cleaning in between the fabrication steps to remove all the residues. And by basically creating this fabrication process over many years, we demonstrated that with wet delamination and also 4-step cleaning method we developed, we can actually achieve high yield, uniform impedance, and artifact-free recording capability with transparent graphene arrays. So how does graphene array look like? So the right-hand side has a representative example that we use in vivo mice experiments. So graphene arrays are basically optically transparent, as I mentioned. So if you look at it under scanning electron microscope, we can see these circular openings are the graphene electrodes. So all the structural components of graphene microelectrodes, including the substrate, the graphene layer, and encapsulation, are optically transparent. It shows a total transparency transmission around 85 to 90%. So it's important to point out that even we deposit very thin layer of chromium on a transparent flexible substrate, it significantly reduces the transparency. In that sense, the transparency advantage that graphene brings is very compelling in the context of building completely transparent microelectrode arrays. So electrode impedance is an important factor in basically designing and choosing implantable electrode devices. So the impedance of graphene in comparison to other conventional electrode materials is relatively large. And that is mainly due to graphene being a single atomic layer material. So graphene exhibits a phenomenon called quantum capacitance, and quantum capacitance actually dominates the impedance of graphene. So it's not a big problem if you are interested in building electrodes as large as 100 microns in diameter. But if we are interested in scaling electrode dimensions to single cell size, then it would result in a large impedance, which would increase the noise. So how can we address that problem? So one of my students came up with the idea that because quantum capacitance is a fundamental problem or fundamental characteristic of graphene, we cannot really eliminate it. If we cannot eliminate it, can we bypass it? So we decided to create a parallel conduction path which can actually bypass the quantum capacitance. So how can we achieve it practically? So it's explained on the left-hand side. So this low impedance bypass path can be achieved by sparsely depositing platinum nanoparticles across graphene. So these sparsely deposited platinum nanoparticles are in electrical contact with graphene. So we still have a single electrochemical surface, but the transparency is still maintained because they do not form a continuous film. So that is the key advantage that we achieved using this sparse deposition of platinum nanoparticles, which is shown to reduce the impedance like 2 orders of magnitude while still maintaining the optical transparency. So using this technique, we actually built high-density graphene microelectrode arrays with ultra-small graphene electrodes. So this is a 64-channel electrode array that shows very uniform impedance. So the diameter of electrodes are around like 20 micron, and the impedance around 200 kilo ohm. So it's also important to mention that these arrays, all of these arrays are designed to be used in mice models. So the total area that is available in the brain of animal is limited. So that actually is the major limitation in terms of the number of electrodes and the total area of the array in our experiments. So after fabricating transparent graphene electrode arrays, the first question we asked was, do they actually affect the imaging? Do they cause any obstacles or reduce the quality of imaging? To investigate that, in collaboration with Anna Delor lab, we actually implanted transparent graphene microelectrode arrays on somatosensory cortex directly beneath the standard imaging window that is used in 2-photon microscopy in vivo experiments. So in these experiments, we used a combination of 2 intravascular tracers along with in a transgenic animal and demonstrated that we can image down to 1.2 millimeters and still the graphene electrodes does not create any obstacles for deep 2-photon imaging. So next step was functional optical imaging. So in these experiments, we actually performed recordings with graphene electrodes from the cortical surface. So the bottom movie shows the cortical waves that are induced, that are evoked by whisker stimulation. As we actually record these waves in individual trials, we simultaneously imaged some cellular activity using 2-photon microscopy from different depths. Here you can see that during these recording experiments, we can actually zoom in an area of interest and directly image like neurons that are directly beneath these electrodes and record their activity in the form of calcium fluorescence as we apply the sensor stimulus. So this multi-model data is very interesting because we have this cellular activity from depth, layer 2, 3, like layer 2, 3 of the cortex neurons, and then we also have the surface potentials that are recorded by graphene in simultaneous settings. So we decided to further understand how these two activities correlate to each other. So when we study this multimodal data, we observed that there is a strong positive correlation between the amplitude of local field potentials recorded from surface with the amplitude of calcium fluorescence that is recorded from layer 2-3 neurons. So that correlation was very interesting because conventionally local field potentials are accepted as only synaptic activity, but in this case, when we record dF/F, the fluorescence change, we are actually recording the spiking activity of neurons in deeper layers. So next, in another experiment, we actually decided to integrate 3 different modalities, including 2-photon microscopy, electrical recordings, and optogenetic stimulation. So in these experiments, we used optogenetic stimulation to excite a certain population of cells, and as the cells increase their activity, that could be detected as a result of, as an increase in the vasodilation or the diameter of the blood vessels using 2-photon microscopy. And as we actually perform optogenetic stimulation, measure vasodilation, we also simultaneously recorded the electrical responses across the array as localized optogenetic stimulation. So for experiments that combine optogenetics with electrophysiological recordings, one important issue is light-induced artifacts. So light-induced artifacts are common in metal microelectrodes, so they can appear as either transients or oscillations in the recordings. Here we have an example showing light-induced artifacts in gold microelectrodes during optogenetic stimulation. So light-induced artifacts are particularly problematic for closed-loop optogenetics applications because they actually, in closed-loop applications, we are interested in recording neural activity in real time to control the light stimulation. And the light-induced artifacts basically can cause false positives. And if we want to basically detect them and filter them, that would increase the system complexity and latency of the closed-loop operation as well. So graphene electrodes eliminates that problem completely because they do not generate any light-induced artifacts. So if we look at the power spectral density of recordings with gold electrodes and graphene electrodes at the bottom, we can see that gold electrodes exhibits huge light-induced artifact peaks at the stimulation frequency and its harmonics. But on the other hand, graphene electrode has no light-induced artifacts because the light-induced currents in graphene are below the noise limits. So that artifact-free recording capability of graphene is very important for designing a very simple closed-loop optogenetic systems. And to demonstrate that, we actually designed a closed-loop optogenetics board by using off-the-shelf components. So, and use this closed-loop optogenetic board to implement some simple threshold detection algorithm, which actually detects the signals using a transparent graphene electrode, and by processing in real time, it can actually trigger LED stimulation. So closed-loop optogenetics enabled by artifact-free graphene is a really important direction because it enables tetherless operation for behavioral experiments, while we will have access to selective and fast control of neural activity, and it can also allow causal investigation of neural circuits connectivity in behaving animals. So do you have any questions? I keep talking without taking any break.
Like the last talk, we can take questions at the end.
Okay, sounds good. So now I'd like to show you another example that we are actually using graphene electrodes in multimodal experiments. But in these experiments, we actually are interested in further understanding the contributions of neural activity that are coming from different cortical layers to the potentials that we record from surface. And to investigate that, we actually performed multimodal experiments where we did 2-photon imaging at 2 different depths, like 50 micron corresponding to layer 1 and 250 micron corresponding to layer 2, 3 of the cortex. So at 50 micron, we mainly have the dense neuropil, axons, and dendrites, no cell bodies, as you can see in the movie at the center. But at 250 micron, we can actually directly image a large population of excitatory neurons and detect their spiking activity using in the form of calcium fluorescence. So these experiments provides us like activity from 2 different layers of cortex, along with the potentials recorded from the surface. So how can we understand contributions from these 2 different activity to the ECOG potentials recorded from the surface? To investigate that, we studied the relative power increase in cortical potentials at different frequency bands. So we basically performed bandpass filtering for the cortical recordings and studied the relative power increase in cortical potentials in different frequency bands during peak activity at 50 micron and 250 micron depths. So our results actually suggested that the activity increase in the superficial layers, mainly synaptic activity, increases the power of cortical potentials at the low frequency bands, such as delta band. But on the other hand, spiking that is coming from deeper layers increases the relative power in high frequency bands, such as gamma and high gamma bands. So these are interesting because it tells us, so the potentials that are recorded from surface is a complex signal. It has contributions from multiple mechanisms, and also those could be actually decomposed by designing multimodal experiments and looking into their contribution to different frequency bands. So I will basically revisit that result in some of the slides that I will explain regarding in the second part. So if we want to use transparent graphene electrodes in chronic experiments, it's very important that they exhibit chronic reliability, they do not degrade over time. So to investigate that, we performed accelerated aging tests in saline at 87 degrees. So we used 4 different arrays and monitored their impedance as a function of days at 87 degrees. So our results shows that graphene microelectrodes, they achieve high reliability, the impedance stayed stable over the course of 1 month at 87 degrees, which corresponds to a lifetime of at least 3 years at body temperature. So showing that the graphene electrodes are chronically reliable in bench tests, next step was performing chronic experiments in vivo. So in various collaborators, we have done a lot of different types of in vivo experiments, but this is one example. Here we were interested in basically recording cellular activity from visual cortex in response to visual stimulus over the course of 2 months. So in this chronic study, the impedance of the array stayed stable over 60 days, and we were able to clearly image the cells at layer 2-3 at 250 micron depth through the graphene electrode. So the imaging window stayed clear. So I'd like to now move to the second part of my talk, which is on virtual recording of neural activity. So what is virtual recording? So virtual recording is an idea that relies on cross-modality inference. It is also based on the principle that the ECOG potentials that are recorded from the brain surface are a spatial integration of extracellular potentials that are generated by the spikes coming from different layers of the cortex and also synaptic activity. So when we perform multimodal experiments with these transparent graphene electrodes, we record ECOG signals from the surface along with calcium activity from hundreds of cells from different layers of cortex. So this multimodal dataset, as I tried to explain in some of the examples of multimodal experiments in the previous slides, consists of like calcium signals and ECOG signals, which are correlated to each other by some hidden nonlinear dynamics. So they both basically correlate to each other. So our idea is basically, okay, so ECOG is a complex signal, but it relates to the spiking and also calcium fluorescence recorded from different layers. By using a neural network, can we actually learn this hidden dynamics and use this neural network to actually virtually record from from the brain where we have only one of the modalities. For instance, if we perform multimodal experiments and train the neural network to understand this, learn this nonlinear dynamics, can we use this neural network to predict cellular activity where we only have recordings from the surface? So that would be one application. And another would be if we only have like calcium imaging, which is most of the case in neuroscience studies, and we do not have the ECOG, can we actually predict cortical potentials from the cellular calcium fluorescence? So that is the idea of virtual recording. So we first tried the bottom one, the prediction of cortical potentials from calcium fluorescence. And to that, we actually used that chronic experiments that I showed in the previous slide, where we recorded calcium activity and ECOG activity in response to visual stimulus, drifting gray pigs. And in this data set, multimodal data set, we have visual stimulation response and spontaneous activity from 16 channels of graphene. So you can see that whenever we have visual stimulus, there is elevated range of gamma activities in the surface recordings. And on the right, there's some representative examples of calcium fluorescence. The blue curves show the mean calcium signal in response to visual stimulus. And the spikes are basically spiking activity from 5 representative neurons that are generated by deconvolving the calcium fluorescence from individual cells. So calcium fluorescence is a slow signal, but by using deconvolution, we can predict the spikes based on the fluorescence activity, which is, again, widely used in calcium imaging. So we actually did it for both awake and anesthetized states, then use this multimodal data set to basically perform decoding of ECOG high gamma power from cellular spikes that we recorded from layer 2-3 neurons. And for that decoding test, we used a neural network consisting of a convolutional neural network with 4 residual layers, followed by a single layer LSTM and a 2-layer multi-layer perceptron. So we trained our model for our data, which is around 1 hour from 16 channel ECOG recordings and calcium fluorescence from 500 to 700 neurons. So the results here in this figure show the ground truth, which is the true ECOG recorded with the transparent graphene electrodes. And the blue curves are the decoded ECOG that are decoded by using the neural network and only using the calcium fluorescence that are generated by the layer 2-3 cells. So our results suggest that our decoding is doing a good job in terms of predicting the high gamma power of ECOG. And it also can actually, in addition to showing good performance for on stimulus, on off stimulus case, it also can actually predict the fluctuations of high gamma power under slow oscillations, which are prominent in the anesthetized state. So on the right, we see this correlation between the ground truth and the predicted ECOG for anesthetized and awake states, which is showing pretty good for basically a neural recording experiment. So the next step was expanding this paradigm to wide field imaging, virtual wide field imaging. So in the previous case, we were interested in decoding local recording, decoding the ECOG potentials from calcium fluorescence from individual cells. But in this problem, we were interested in, can we actually decode or virtually record cortex-wide neural activity from local electrical recordings? So in this case, we performed a multimodal experiment, which does not generate cellular calcium, but it looks at the calcium activation across the entire cortex. Here you see that the graphene electrodes are implanted on one corner to record local ECOG activity. And in these multimodal experiments, we simultaneously recorded local ECOG potentials along with wide field calcium imaging. So similar to the previous case, we know that the locally recorded neural potentials contain rich information regarding the large-scale neural activity. And our goal is, again, to learn this hidden nonlinear dynamics between the local electrical recordings and the wide field calcium imaging to basically virtually record the neural activity across the entire brain. So for that, we used a neural network model that is consisting of a bilayer LSTM sandwiched between two linear layers. And in the input of our neural network, we have ECOG potentials from 16 channels that are decomposed into different frequency bands. And for the output, we have the wide field calcium imaging. And for this test, we were interested in two different problems. So the first problem was, can we actually decode the mean activity of multiple cortical regions? So cortex have a lot of different functional regions, like motor cortex, sensory cortex. Can we, by only looking at local ECOG, can I predict the activation level of sensory cortex on the other hemisphere? So that is the test one. And for test two, we were interested in decoding the pixel level activity from ECOG potentials. And by using that pixel level activity, can we actually reconstruct the cortex-wide activity as a function of time? So these two tasks are basically achieved by using very similar neural network models. On the left, we have the results for task one, showing predicted calcium fluorescence and ground truth. The predicted one is shown in black, and ground truth that is recorded with wide field calcium imaging is shown with red. So we can see that our neural network does a good job in terms of predicting the local activation of 6 cortical regions as a function of time. And when we look at the correlation between the predicted fluorescence and the ground truth as a function of different frequency bands, we can see that the highest correlation is achieved when the information from all frequency bands are used, suggesting that the neural dynamics connecting these two modalities to each other is provided. It's important to capture the information from all frequency bands to understand that relationship between these two modalities. And on the right-hand side, we have the results for pixel-level virtual reconstruction of neural activity. So the left one is basically the ground truth, and the right one is the predicted calcium fluorescence. So the ground truth is recorded by optical imaging, and the predicted one is predicted from our neural network by only using the local ECOG potentials. So showing pretty consistent prediction of neural activity as a function of time. So these results basically suggest that this virtual recording can actually provide a unique opportunity by using multimodal experiments and cross-modality inference to potentially develop minimally invasive recording paradigms for recording neural dynamics across large areas in the brain. So we continue to these research efforts to further expand to other multimodal experiments and also using cross-modality inference with different modalities. So in the last part of my talk, I will tell you about a new neural electrode technology that is developed by my lab, Neuromorphic, to study the neural circuits that play important roles in learning and memory formation. So just to give a little bit of introduction on the problem that motivated us to develop Neuromorphic probes is basically learning and memory consolidation in the brain. So in the brain, there is a subcortical structure called hippocampus, shown here with blue. So hippocampus is an important structure for learning, memory formation, and navigation, and that's well known for more than 100 years. And I mean, there are many models of learning and memory formation, but according to a popular model, which is two-stage model of memory, so hippocampus basically serves as a substrate for temporal storage of newly acquired information. And over the time, newly acquired information is transferred to the cortex for long-term storage. So, and according to this two-stage model of memory, it's very important, like the communication between the hippocampus and cortex is very important. So experimental work that is involving learning, memory, and some behavioral studies show that there is an oscillation in the brain called sharp wave ripples, which could be a potential substrate, potential mechanism that can facilitate this memory transfer or memory consolidation between hippocampus and cortex. So sharp wave ripples are generated by hippocampus, and they're the most synchronous population pattern in the mammalian brain. And further experimental evidence suggested that indeed sharp wave ripples could be a mechanism for transferring information from or coordinating the transfer of information between hippocampus and cortex. So in studies with rodents, during sharp wave ripples, it was shown that previously learned information is replayed in a compressed time scale during the sharp wave ripples. That could be a potential mechanism, again, to consolidate the newly learned memories from hippocampus to cortex. So if you look at this cartoon example, so during exploration, specific cells in the hippocampus of mice, they fire sequentially in behavioral time scale as the animal travels across space. And the same spike sequences are replayed in a very compressed time scale, which is on the order of 100 milliseconds, in forward and reverse orders during sharp wave ripples when animal is in basically sleep or resting state. So that has been shown by many labs, and like every day, the interest in sharp wave ripples and studies investigating the mechanism of sharp wave ripples is basically increasing. And so most of the knowledge of sharp wave ripples and the spiking of cells, they rely on electrophysiological experiments that basically focus only one or two regions in the cortex. So if we really want to have a big picture, better, like large-scale understanding of communication between cortex and hippocampus during sharp wave ripples, we really need an experimental paradigm where we can record the activation of cortical regions across the entire cortex while we actually detect sharp wave ripples from hippocampus. So there is no technology suitable for that, for the reasons that I explained. So, and the newly developed neural electrode technology, Neurofittim, is a great fit to investigate this question. So Neurofittim, the long form is flexible, insertable, transparent microelectrodes. It's a very odd name, but it turned out that finding a name for a neural probe is more difficult than naming your child. So I apologize for the probe name, which is difficult to pronounce, but it's already published, I think. So Neurofittim probes are designed to perform multimodal experiments to record from deeper cortical layers or subcortical structures during optical imaging. So in this particular example, we are focusing on this sharp wave ripples and how it basically coordinates the communication between cortex and hippocampus. And three key characteristics of Neurofittim are important to enable such experiments. So the first one is flexibility. So Neurofittim probe, including the probe itself and shank, are completely made of flexible materials. And the flexibility of probe shank is very important because once it is implanted, we can bend away to the side so that we can lower the objective, microscope objective for imaging. If we were to use a silicon probe, so we cannot really approach the objective to the cortical surface to perform imaging. In that sense, flexibility of the probe shank is very, very important for doing like multimodal experiments with the depth probes, insertable probes. So transparency of the shank is also important, not to create any shadows or block the field of view, but our shank is completely transparent. So you can see on the right, it does not affect imaging. And in addition to that, the flexible probes can actually be implanted without using any shuttles, no microneedles or bioresorbable stiffening layers, and that is important to minimize the tissue damage. So how is shuttle-free vertical implantation is achieved? So in order to do so, we actually carefully engineered the geometry of the probe and the length. And we actually, in our design, added some additional micromanipulator pads to optimize the insertion force against buckling during implantation. And as a result, we demonstrated that we can actually successfully target hippocampus with minimal damage to the hippocampus and above cortical tissues. So we use Neurofittim probes for recording from hippocampus, but because they're microfabricated, they can be built in different configurations. For our collaborations with other labs, depending on the experimental needs, we actually change the electrode density, spacing, or the probe shank length, again, depending on the target animal experiments. So to investigate the communication between hippocampus or coordination between hippocampus and cortex during sharp wave ripples, we performed multimodal experiments in mice. So in these multimodal experiments, neurofilm is implanted to hippocampus CA1 layer, and we actually recorded sharp wave ripples along with cellular spikes in the CA1 layer, neuron layer of hippocampus. And in these experiments, we simultaneously imaged various spatial patterns of activations in individual trials or in individual recordings of sharp wave ripples. So as you can see in this representative example, electrical recording of sharp wave ripple looks rather similar most of the case, but it can actually result in, it can coordinate very different type of spatiotemporal patterns of cortical activation simultaneously in individual trials. So this slide basically shows some examples of single units that are recorded with neurofilm probe. So this is like 21 different neurons recorded across different channels overlapping with the CA1 layer. In these experiments, we recorded both the spikes, the sharp waves, and the ripples with very high signal-to-noise ratio, which made our lives easier in data processing, of course. So the first question we asked in this multimodal experiments, okay, hippocampus and cortex communicate, but which one leads this communication? So to investigate that, we studied individual trials of sharp wave ripples and the cortical activation. And we found that that communication is bidirectional. So either cortex or hippocampus can lead that communication. But in most of the trials, we observed that at least one cortical region has an activity onset that precedes the sharp wave ripple onset in the hippocampus. And that fraction of sharp wave ripples initiated by cortex versus hippocampus depends on the cortical region as shown in this figure. So the next question we asked, okay, sharp wave ripples are high frequency oscillations from hippocampus, but are there distinct cortical activation patterns that reproducibly observed during sharp wave ripples across different animals? So to investigate that, we basically used our multimodal data, and we used tensor component analysis for dimensionality reduction. So we have this 3D data where we actually decompose it to region factors that are reflecting the spatial activation, time factors reflecting rapid circuit dynamics, and event factors that are explaining the trial-to-trial changes. And tensor component analysis identified 8 distinct cortical activity patterns during sharp wave ripples, which is commonly observed across all the trials and all the animals. So some of these patterns are focused on anterior regions, such as motor cortex, and some of them are focused on posterior regions, such as visual cortex, and they are spatiotemporal, which means some patterns involved activation of cortex first, while some patterns included like sharp wave ripple first, followed by activation of the cortical regions. But the important message is that we were really surprised at showing that there are 8 patterns of cortical activation repeatedly occurring across many trials in all the animals in these experiments. So the next question we asked, okay, we recorded a lot of spikes from hippocampus. Can we actually understand how do these neurons behave during different cortical patterns? So when we study the activation or the spiking activity of the neurons from hippocampus CA1 layer, we observed that hippocampus neurons during individual sharp wave ripple events are differentially modulated depending on the cortical activity pattern. And as a result of that selectivity, we were able to demonstrate that we can actually predict or distinguish a large fraction of cortical patterns by using the firing activity of the hippocampal neurons. So that is suggesting that there are distinct populations in the hippocampus that are being active or that are modulated differently by the ongoing cortical activity in the cortex. So the experimental findings that are enabled by neurofilm technology are summarized in the slide. So we basically demonstrated that hippocampus and cortex exhibit bidirectional communication. And they do not communicate in one way. They exhibit different and distinct patterns of cortical activation patterns during the sharp wave ripples. And we also demonstrated that some distinct subsets of hippocampal neurons are modulated differently by these cortical patterns. So these findings suggest that hippocampus and cortex communicate through different information streams involving different subset of neurons and activations of different cortical regions, depending on potentially the context or the cognitive processing that are going on during that sharp wave ripple event. So I'd like to conclude my talk here. I hope I did not go over my time window. So I like to emphasize again the multimodal experiments that are enabled by transparent neural probe technologies are really interesting to investigate the information processing going on in the brain or any other basic neuroscience questions by combining the strands of different modalities, including optogenetic stimulation, multiphoton microscopy, and artifact-free electrophysiological recordings. And I hope to continue the research in that area and develop new technologies and also demonstrate their applications to interesting neuroscience problems in the future. So I like to acknowledge my students. They do all the work and I just present their work, and my collaborators and funding agencies as well. So I'm always actively looking for motivated PhD students and postdocs. If you're interested in, email me. Here is a link of our group website. So thank you so much for listening. I would be more than happy to answer if you have any questions.
Thank you so much for the outstanding talk. Let's open up the floor for any questions. Feel free to either type them into the chat or to raise your hand, your virtual hand. So I'll get things started. But actually, we have hands up, so we'll come back to my question. Professor Thakur, feel free to unmute yourself and ask a question.
Hi, Duygu. This is great talk, incredible work. Can I ask you a question about your ECOG array? If you make those high density, are you able to pick up the neural activity as it's been claimed with, or do you still have to go with the depth electrode? And if you have time, the second question is, are you able to insert your thin electrodes in the sulci?
Yeah, those are great questions. It's great to see you, Nitish. So yeah, I think your first question, if I understand correct, can we record units from surface?
That's what I'm saying. When you have a very high, small separation, bipolar, very thin, clear contact,
Yeah.
right? Because these are very thin.
Yeah, we tried it. Yeah, we tried it. But I mean, we definitely record multi-unit activity, independent of like the size or spacing. Even with 100 micron electrodes or 20 micron electrodes, we can record multi-units from the surface. But regarding sortable units, even we built like 20 micron electrodes with 20 micron spacing, very dense microelectrode array from the surface. We could not achieve sortable units. I mean, we record some units, but they're not sortable. So they're probably coming from multiple sources. Okay. So it's not a replacement to depth recordings. That was my conclusion. I was very hopeful. Yeah, and our electrodes are very flexible. They can be inserted to sulci. I mean, we use them over and over, like in chronic studies, and if it is not damaged, they are reusable. So we never tried to insert it to sulci, but probably it is doable. So I wouldn't expect any issues regarding that.
Thank you.
There's another hand up. Feel free to unmute yourself and ask a question.
Hi, okay. This was amazing. It has really helped me a lot. I have a little doubt. Could this be used for detection of brain tumor, enhanced, version of detection of brain tumor, or is it a different thing? I just had a little bit if this could be used in such type of spectrum too?
Probably not necessary. Like there are many ways of detecting brain tumors in imaging. So probably electrophysiological recording or multimodal experiments would be like it would not be necessary in the context of brain tumors, but we do use them for organoids. Like we implant brain organoids in vivo, like human brain organoids in mice. And then we record activity from brain organoids and the cortex using this technology. They're not tumor, they are like opposite of tumor, replacement of brain tissue with an organoid. But yeah, I mean, any excitable tissue which generates electrical activity could be potentially recorded by using either these electrodes or other electrode technologies.
Thank you so much for clearing my doubt. Thank you.
You're welcome.
So there's a question.
There's a very good question in the text chat box about PDOT versus graphene.
So the question in the chat says the differences or trade-offs between graphene and PDOT. Is there a need for platinum nanoparticles with PDOT?
I'm not an expert on PDOT. I mean, PDOT is a good coating, right? So to reduce the impedance, but as far as I know, to reduce impedance, it needs to be thick, which makes it non-transparent. So for our case, it's not only the transparency of electrodes, it's also the transparency of the wires. Because in a very high density array, your electrodes are, occupying some space, but most of the field of view or the area is actually occupied by the wires that are connected to electrodes. So making the wires transparent is very important, even more important than making the electrodes transparent. In that sense, PDOT would not solve it, right? So PDOT only reduces the impedance for electrodes. And we are really interested in chronic reliability. So I'm not sure about chronic reliability of PDOT. So that is, I never used PDOT as a coating in our electrodes. So I cannot answer that question. But the short answer is PDOT is not transparent. So it cannot be a replacement to graphene. But if your goal is to only record neural activity with high SNR, I would just go with platinum, iridium oxide, platinum iridium, which are electrode materials in commercially available medical implants. So they would be the most reliable. You are welcome.
So I have a question about your optogenetic stimulation probe, the little micro LEDs. What is their field of excitation and how selective are they for individual neurons?
Yeah, that's a good question. So, if it is fiber-based, so that was a very simple demonstration where we used micro LEDs commercially available and coupled it to optical fibers to basically stimulate depth. So it depends on the power, the proximity of the light output, and the area. So if selectivity is really important, perhaps like 2 photons would be a better option for optogenetic stimulation, like really individual cell level selectivity. But with that, with our approach, it's just like a fiber. So it's gonna have like the diameter is around 300 micron. So it's gonna illuminate a cone, which is on the order of like 1 millimeter by 1 millimeter. So it depends on, again, the power and the light output of the fiber tip. So it's if spatial localization is very important, that would not be a good approach.
Thank you. Are there other questions from the audience? Great. Well, let's thank our speaker very much for an excellent talk.
Thank you.
And this may be a good way now to segue in our rest of the discussion. So this is open floor.
One more question did actually come into the chat before we conclude. There's a question that says, how was hippocampus recording correlated with cognition and memory?
So hippocampus, so in our study, we did not correlate it with cognition and memory, but there have been a lot of experimental research that is actually involves behavioral experiments where animals are trained to perform a certain test, like learn a certain test, perform it, to basically study learning. So, and in those experiments, so the spiking activity of hippocampus and the sharp wave ripples, they have been studied in the context of cognition and memory. The results that I showed today, they only focus on communication of hippocampus and cortex during sharp wave ripples, which is known to play roles in memory consolidation. But our experiments did not involve behavioral or learning in the context of like training the animals for certain tasks. So that could be a good next step, right? So applying our technology to a behavioral study where we actually monitor the memory as the animal learns a certain task and see how actually sharp wave ripples plays roles in learning and behavior. So that's a good next step. Thank you.
It looks like one more hand came up as well. Please feel
Yes,
free to
the
unmute.
question, I'm Mahmoud Auda. Thank you very much for the very nice presentation and very wonderful work. I have a quick question about the closed loop optogenetics, the micro-LEDs arrays that you have used. You are using the micro-LEDs to stimulate with the light for the optogenetic. How to record it? You record it by microscope or you record by electrical electrodes on the graphene itself? I'm asking about the optics or record electrical.
So we needed to use graphene electrodes, right? So the stimulation is done micro LED coupled to an optical fiber. And then the recordings they needed to be done by graphene, because if you do not use graphene, there will be light-induced artifacts. And as I try to emphasize, light-induced artifacts are false positives, right? So in closed-loop operation, you really do not want to deal with a lot of false positives. So the recording is done by graphene electrodes, and the stimulation is done by a micro LED coupled to an optical fiber, which to stimulate deeper regions.
Yeah, thank you.
Did that answer your question?
Yeah, exactly. Yeah, thank you very much.
Oh, there is one more question. The electrodes, can they be wrapped around nerves? They can be wrapped around nerves, but we have never tried it. So we actually used them in many experiments that they needed to be bent severely. So they can, I would assume they would still function fine, but we may need to just change the design, maybe add some holes and sutures to fix them in place. But I think they can be wrapped around nerves potentially, but we never tried it, so. Any other questions?
So we have the last part of the session is now an open floor discussion with both speakers, and the entire audience is welcome to chime in on general advances, technology advances in basically neurotechnology for unobtrusive access to the brain in bidirectional fashion, recording stimulation, and to the body in general, right? So, and so the question here is really how, and which was very much addressed by both talks here, right? So how can we improve technology, not just in the conventional means towards solving one particular problem, in an isolated fashion, but really capture all different modalities that you have in brain, mind, and body in as unobtrusive means as possible. So without intruding on the comfort and the natural operation of the user. So that it really becomes available 24/7 and can really help towards developing better strategies for either therapies or just general strategies for maintaining healthy and well. So and this is open floor. So we'd like this to be as interactive as possible. And Nitish, I see your hand raised, so please go for it.
You know, it's amazing what both the speakers and of course got what you're doing. But you know, then these things are not broadly available. And I want to check with your experiences, all the speakers, whether you're able to find support from NIH or other means to create a resource where you can share your electrodes, you know, like Intan is available to all of, so that everybody can, you know, create that. It's a commercial solution. I know Cindy Chestek has distributed some electrodes through a contract. So I don't know whether any of the speakers have experience sharing your electrodes or circuits or integrated solutions.
Oh, I can maybe answer that. So I share my electrodes with a lot of labs, both in the US and in Europe. Because it's a research material, right? So it really requires it's not like a commercial product with like a list of things to do. So it really requires a collaboration, right? The other party really needs to have a good communication with us to get it working. So, I mean, in 90% of cases, so like other labs get it working. So I sent them to Boston University, Columbia University. They all use them in their experiments to London. So, and to Stanford. But there are also cases that I just ship the arrays and never hear back. So, which turns into not a sustainable way of providing technology to others. But I agree that like seeking some NIH support for dissemination of technology is a good first step. But I feel in the long run to bring it to like a technology similar to like the IMEC probes, right? So neuropixel probes. So we really need help from a foundry to fabricate them and make it broadly accessible to the research community. So even just having NIH dissemination grant, I mean, we can fabricate and disseminate to many labs with it, but to make it really freely accessible to everybody, I think that should be like a commercial solution.
So I'll take you up on it. I send you a text message.
Oh.
I can also speak to it. I previously had a company where we translated some of our research and initially started with neuroscience research products. In fact, micro ECOG arrays, as well as our integrated circuits. So for sure, anytime you ship these quote unquote products to anybody, there's a lot of customer support required just to get things even set up in a new lab and environment. And that requires full-time staff if you're going to ship it to more than one lab, basically. And so I strongly agree that this is very much a commercial endeavor, that there has to be documentation, there has to be customer support, there has to be a user interface, associated software. And this is something that's very, very difficult to incubate within a research laboratory where students are very focused on research as opposed to product development. But the one nice thing is that there are commercial partners out there. We worked with BlackRock Micro as well as White Matter LLC to actually distribute products, and they have their own kind of support and staff for the distribution and support of such products. So you can form commercial partnerships to do this type of distribution.
Let me also share here from my perspective that being an academic, I've been in academics for many, many years, over 25 years, but also having ventured into a startup, this is Cognionics, which is now called CGX, so developing dry electrode technologies. It's actually quite accessible for academics or people that have usual training, whether it's in engineering or neuroscience, to start and make an impact in the field. Unobtrusive technologies not only are really transformative in they can really help health monitoring in a much less obtrusive fashion. But the technology in general can also be simpler and basically calls for less high-tech development. In fact, as simple as a printed circuit board would even function as a way of interfacing to the brain and the body. In fact, there's a whole community, OpenBCI, that is developing sensors for brain recording with EEG. And those sensors also work for measuring other signals, ECG, EMG, etc. So there's definitely a community out there that is able to really access technology and build this technology from the ground up. And so we always welcome young generations of people, students, to take initiative and do more of that to make all these technologies more accessible and having greater impact in health and wellness. There's a question. So yes, Zafar.
I'm not in this particular area, but I'm retired. I think you see that there are not many questions asked from the audience, even though we have 125 people here. I think the symposium will have more benefits if, for example, in our case, you are asking the individuals to talk about what their research is, and then the speakers talk about their special activity which they have done. I suggest that it will be, if they're talking about sensors, they should talk about the intrusive, non-intrusive, those sensors which are already available. And then from there, they move on and say, what we are doing this thing, it is, advancement and things. Then the audience will have more understanding of what is going. Same way, the processing of those signals which are coming, how they are really being processed now and what in the research they are doing so that it is going to enhance also the applicability of those availability. I think that way it is going to, you will see more questions coming, more understanding of those, rather than just you ask me and say, can you give a presentation? And I will give my presentation, what I'm doing. May not be relevant to everybody, but if we go through step by step, providing, I think that will be much more useful for the audience. This is just my humble opinion.
Thank you. And we definitely want great interactions. In fact, one of the experiments here that we're doing over this Zoom interface is to see how far can we stretch this online virtual interface. Supposing we're all connected across the world, and we had people almost from every continent represented here. Some were staying awake in the middle of the night on their continents to join in. And so, yes, so please, we very much encourage these live interactions. Maybe we're all warming up still, and we'll have more interactions coming. There'll be some breakout sessions later again for the posters, and so please don't be shy. And so this is between the panel of speakers and the attendees. So Duygu, so you have a beautiful technology for multimodal sensing, and it's quite unique to have the capability of really going between neural activity, basically imaging neural activity as you would do optically, and then also have the electrical activity available at the same time. In fact, you were showing some quite impressive results that you can even infer this imaging modality or predict it from the electrical activity. So how do you see this? So this opens up tremendous opportunities, right? So how do you see this pan out for, say, health and wellness in terms of new types of unobtrusive technologies that can help with therapy or just for general brain cognitive monitoring, right? And so the key here is that you can get great temporal resolution with ECOG, right, or electrical recording, and you can get great spatial resolution with optical recording, right? And so how do you harness both of them and get something as super great as, say, MRI, but now using basically unobtrusive wearable technologies?
Yeah, that's a great question, George. So that's what we have been thinking for many years. Like, what are the, I mean, these multimodal data sets are so rich. So how can we actually utilize them for either like medical or also like neuroscience applications? So if you specifically look at that like virtual like inference, cross-modality inference case, so it allows us to basically expand the spatial extent of recording, right? So for instance, you can record the ECOG from one area in the brain. Like if you think about the human recordings, right? So it's not possible to cover the whole cortical surface with ECOG electrodes. That would be extremely invasive. So if you could actually apply such cross-modality inference to ECOG recordings in humans, so you can record ECOG from only a small area in the brain without removing a lot of skull, and then basically use those recordings to infer cortex-wide neural activity by only having those local activities. So that doesn't need to be done only by optical, right? So it could potentially be done with fMRI too. So it's cross-modality inference. So it's applicable to modalities which are connected to each other through neural dynamics. And the other one is like these imaging experiments that I presented today. Like they are great, right? So you can do like hundreds of cells, so fancy, or you can do the whole brain imaging, but still you can actually, that requires animal to be head fixed, right? So you fix the animal under the microscope. So that's not desirable for behavioral studies. So instead of doing that head fixed experiments, so you can again use this cross-modality inference where you actually do that experiment once, collect all the data, train your neural network, and then for the next set of experiments, you can have the animal freely behaving, and you only use the recordings to infer the imaging data. So that would be like a great application for optical imaging in neuroscience studies. And in both cases, it's basically reducing the invasiveness. So that, of course, requires generalization of the model, right? So our model actually needs to be generalized. So it needs to work across animals, at least, I mean, I do not expect it would be applicable across species. So we cannot use mice model for human, but at least like across animal generalization is the first step to make it like usable for the applications I mentioned. So that's a great question.
That's great. So you have several more questions. Now we're running at the end of the session. So maybe just a few more quick questions, because we don't want to get too much into our poster highlight the session. So so maybe one more quick question. I see some hands raised. If not, so you can please put your questions in the chat and we can continue discussions over the chat window. So with that, this ends just in time, our first mini symposium. And so now we're ready to go to the exciting poster highlights. So Nitish and Mariam, so please, you have the floor.
Okay, I think I'm the one here, and potentially I'm hoping Jim Milin will join. So hello, everyone. Welcome to the poster session. So, we have several teams, students mainly, who have put together wonderful posters. And what we're going to do is perhaps some rapid fire, one slide overview by the students. And, they'll have to come up quickly one at a time and present. And then after that, after 15 minutes, we will go into a breakout rooms. So that way you get to meet with them, okay? So right now, what I'm going to do is do the screen share, okay? And then later on, I will do the breakout. So my screen share will bring up the posters that have been contributed. I just received them hot off the press from Gert and the team. So I know he's obviously wonderfully multitasking. So thank you. And sorry, some of you have your hands raised for asking the questions. So that should teach you that ask your questions quickly. Don't be shy and don't wait. Okay. All right. So all the people who are present who wrote the posters, I hope you can see the poster being shown. Gert, you can see that, right? My screen share?
Perfect.
Okay, good. So this will come up one by one. Whoever is the speaker, you have about 1 minute, something like that. So present, if somebody doesn't show up, then we have a little extra time. Okay, so with that, and I'm doing this, thank you, Gert, for organizing the conference, a lot of the program chair, and Mariam is my co-chair, but she has other commitments, so she will join tomorrow for live poster. So guys, please don't forget that session tomorrow. Okay, so let's begin with this first one on polymer implant electrode foundry. Is the student author there?
Yes. Hi, can everyone hear me all right?
Yes, go ahead. You have a minute.
Hello, everyone. My name is Key Schulten. I'm from the University of Southern California. My poster introduces our new center, the Polymer Implantable Electrode Foundry. We work to develop minimally obtrusive neuroelectronic interfaces by microfabricating electrode arrays that are smaller, softer, and more flexible than traditional devices. And we accomplish this by applying semiconductor manufacturing techniques that thin film biocompatible polymers.
Sorry.
No, it's all right.
My mistake.
The Pi Foundry is a shared resource. We help build researchers custom devices based on their own needs for that application. Our poster describes a little about what we need to do and shows some recent examples of our work. Thank you.
Wonderful poster and a good reason to come and visit you so that people can use this technology. Wonderful. Next one, non-invasive neuromodulation. Are the speakers there?
Yes. Hi.
Go ahead.
You hear me okay?
Yes.
Good.
Hi, this is Matthew Smith from UC San Diego, and just briefly giving an overview here in this slide of Faraday's law in action in terms of non-invasive neuromodulation, from a scalable approach down to very low magnetic fields all the way to high magnetic fields, and including implant technologies. So this is fundamental research involving complex multi-loci and multi-site current patterning, which is in its nascent stage in classical neuromodulation. You've heard it as TMS, transcranial magnetic stimulation. It offers precise, rapid, repeatable steering. And we also offer a very practical excitation synthesis method to generate these complex excitation fields about 1 to 2 centimeters down in the brain. Some of this is FDA approved for depression and PTSD. Thank you.
Wonderful and good time management, and another reason to go and see this poster to speak with you. I would like to go there. Okay, the next presentation on EEG alpha phase synchronized TMS. Are the speakers there? This is from Paul Scheida's lab, Shao or any of the authors of the poster there? Okay, well.
Yeah, I'm here.
Please go ahead, don't wait.
Yeah. So our study, so we use the closed loop EEG alpha phase synchronized RTMS treatment to help the patient, to help especially the treatment resistant MDD patient to have to achieve their higher treatment efficiency. So basically the idea is that from our previous experiment, so the integrated the MIEG TMS system, the FET system, so we can measure the corresponding phase that can maximize the participants' both activation within the ACC area. And then by using that phase, we have two group randomized distributed. One of the group received the treatment that with their alpha phase synchronized to their previous phase that we measured about the measure that can maximize their both activation. And then by doing that, we can compare those two different conditions to see how the phase synchronized treatment gonna improve their treatment efficiency or not. So one of our highlights of the poster is that our ability to integrate the closed loop for the alpha phase locked TMS triggering is very unique, and also a lot of other study for their closed loop system, they are still under the development stage. But for us, we're already in the next level. We can already apply this in our clinic treatment. And for our study, we gonna unblind our study very soon in next year, January, so we can see whether. So for us, currently, we can only investigate some like brain dynamics post the RTMS treatment, but we don't combine this with some clinic result yet. But in next year, we can combine this with our clinical result to see whether this phase-locked treatment can improve their treatment efficiency or not. Yeah.
Thank you for summarizing so much work so quickly. I know some of you are raising hands. We won't take any questions right now. You will go later on to breakout rooms so that you can speak with each of the poster presentation as you wish, okay? And there are 4 breakout rooms, so you'll be jumping from one breakout room to another. So we'll go to the next one. This will be in breakout room 2. By the way, note that, okay? So that any poster that you like, you have to note which room it's going to be. So this is about EEG and BCI and virtual reality. All right, so the next presentation on Apollo distributed virtual reality BCI. Are the speakers there?
I'm here. Can you hear me?
Speak a little loudly. You're barely audible.
Awesome. How about now?
Yes.
Okay, great. So hello, everyone. My name is Ino, and today I'm going to present about our poster, Apollo Distributed Control Test, or ADCT for short. And it is a virtual reality brain-computer interface for virtual spacecraft navigation. So we proposed the ADCT, which is a team-based VR task to study how pupil dynamics change vary under multiple task-related dimensions, including communication bandwidth, for example, no communication or free communication, and difficulty levels like easy, medium, or hard task, and also the player's role in the task.
Thank you. Nice work. And
thank you.
You'll definitely attract people to your poster. Okay, next one. The speaker says multifunctional rehabilitation through EEG and feedback.
Yes, and thank you for letting us speak. It is a student-led ongoing effort to exploring kind of an open source development of a prosthetic in conjunction with the VA and led by veteran students to create more available and accessible, we'll call it a BCI interface for prosthetic systems.
Excellent, student-led effort. That's great. And open source is even better. That'll lead to collaborations. Thank you. Okay, next one is biometric subject identification using EEG time frequency. Are the speakers there? This is a group from India, so I'm sure we're dealing with some time zone challenge. Not too late, about 11 p.m. there, maybe later. Are speakers there?
Yeah.
Okay, I'm sorry, looks like they're not, so we'll have to move on.
Excuse me, sir. Can you
Are you there?
Yes, sir. Yes, sir. Sorry.
So please speak up and don't wait for invitation.
Yeah.
I will move on. So, and you're not audible, so speak loudly.
Okay, sir. So
No, you're still not audible, so you need to speak loudly or come closer to the microphone.
Okay, sir. Our work is related to using or trying EEG to be used as a biometric recognition system, wherein we have come across different biometric systems like physiological biometrics, but it has got some disadvantages. So we tried using EEG-based biometric recognition by collecting resting state, and also in the next proceeding work, we tried with some task-based EEG and tried whether we can able to distinguish different persons based on the EEG traits. Yes, sir.
Okay, wonderful use of EEG for biometric. Quite interesting. Thank you. Thank you for joining from far away. Okay, so next one is from nearby where the meeting is. Signal reconstruction on gaze-related EEG and virtual reality. Are the speakers there?
Yes, can everybody hear me?
Yeah,
okay,
a little louder would be better. Go ahead.
Okay, so in this project, we are going to demonstrate how we can reconstruct EEG signal in the mobile virtual environment. So previous study, people usually ask the subject to have a fixation on screen first, and then they present a stimulus. That's how we get our stimulus-related potential. Or we ask the subject to have a response, and then we have that response-related potential. However, that will not be the case if we let the subject to freely looking in the VR environment. So in our study, we try to demonstrate that the previous fixation algorithm using in the 2D space, like the well-controlled lab environment, will fail in the VR, and how we can go around with that and reconstruct the signal. Yeah, thank you.
Wonderful job. Thank you for presenting succinctly and quickly. Okay, so we're moving to breakout room 3. So again, please keep in mind that if any of these posters interest you, go to the appropriate breakout room. Okay, so this is about emotion and compassion in the spirit of this mind-body conference. So closed loop mindfulness for physician trainees. Are the speakers there?
Yes, good morning all. I'm Satish Jaswal from NEET Lab. So in this currently ongoing longitudinal study, we are examining whether a digital delivery of mindfulness app can change or protect physician trainee students from burnout or can enhance the empathy, self-compassion, resilience, and also could change their cognitive functions and basically improvement in their cognitive functions. So in our data from like 14 participants, we found that using this cognitive tool that has been developed by our team called Brainy, and that has all these, modules that measures different cognitive functions such as inhibitor control, working memory, conflict control, and also an interoceptive attention task where they have breathing count with the 2-tap. So in our results, we found that there was indeed their increment in their resilience and well-being, and there was similar trend in their empathy and self-compassion level. In our cognitive measure, we mainly found their improvement in their working memory span, and there was also increment in their consistency and faster speed. In overall, and in some cognitive functions, we didn't see any effect of mindfulness that's showing that it could be
so can you wrap it up? This is not the whole poster. You have 1 hour to explain in detail. So
overall, we saw that a brief mindfulness meditation can alter or improve the cognition, subjective measure, and cognition in many students.
Thank you. It looks excellent that you got good results. Good for you. Okay, so the next presentation on EEG eye gaze decoding for aesthetic emotions. Are the speakers there?
Yes, hi. So we had our participants viewing paintings at the San Diego Museum of Art, while we derived a mobile EEG and eye tracking data using a mobile EEG system and eye tracking glasses. So the participants were able to view the paintings freely and resynchronized all the data and calculated fixation-related potentials in the EEG, time locking to the onset of fixations while viewing the paintings. And we identified different FRP amplitudes for different types of fixation patterns and viewing behaviors, and found that this effect partially depends on emotional states evoked by the paintings.
Terrific, and you get to go to museum, even better. Thank you, nice presentation. Okay, next presentation on EEG spatiotemporal attention discrimination. Are the speakers there?
Hi everyone. In this work, we use the EEG information while people are rating different emotional videos. So we get benefits from the location of the EEG data over the scalp, their connectivity, their adjacency. And we model them based on the graph Fourier transform. Then we use the neural networks to extract the information in the spatial and temporal domain by getting emphasized on the time steps that may have much more information than the others. Our results was really good compared to the state of the art. So I'm really happy to meet you if you are interested.
And good job, and very interesting graphic. Good job with the graphic too. Okay, so the next slide, next one is effects of champion.
Sorry to say, but the slide was updated in the background in the last 5 minutes.
Oh, I'm so sorry. Then I have a little older version. Please go to the poster session so that you get to see the real thing. May not be able to switch so quickly. Sorry about that. Okay, so the next one is adaptive resonance modeling of emotional episodic memory, etc. Speakers, are you there?
Do you want me to comment on the previous?
You may. I don't know if I can substitute. Sorry, and Gert, you can tell me if we can afford the time. But
that's okay. I can comment without it.
Go ahead. Go ahead quickly.
Let me actually share my screen here.
Okay, I will stop the share and you can take over. Sorry, speakers. This is happening just in time. We had some contribute very recently, and I think I had the latest draft, but apparently I didn't.
Is this the correct version?
Shadi or the speaker, is this the correct version?
Yeah.
Please, then do you want to explain it quickly?
Actually, as I mentioned before, we use the EEG recording data and then model it based on the HSSC matrices and the graph Fourier transform methods, and then use the transform data as the input of the neural network. Our network consists of 2 parts, the parts that are responsible for encoding the spatiotemporal information, and 1 part that are responsible for the extracting the temporal just information. And here we also showed that the learned parameters, the feature maps that were learned during the spatiotemporal encoding part, and our results was consistent based on the emotion recognition EEG literature, that also the parts that the network extracted was consistent with the parts of the brain that are responsible for emotion recognition.
Very good. Thank you. Gert, you'll have to advance the slide since you now have the control. Again, we seem to have.
So can you hear me? Oh.
Go ahead.
So this is also another student-led effort, collaborating with both research institutions and a medical university, exploring how we can do a proof of concept to see if simple stimulant detection impacting emotion detection, applying artificial intelligence and neural networks, could be translated to determining the effect of medication on emotion detection and other features. So it's a proof of concept as a follow-up presentation to the medical university for support.
Thank you. Again, congratulations on student teamwork. All right, we have another presentation from India. So thank you for presenting from so far away. Are the speakers there?
Yes, I'm here.
Go ahead,
can I go
please.
ahead? Yes,
yes please.
Hello, this is Ilakya from Assistant College of Engineering, India. And this poster is about episodic memory encoding and recall modeling using adaptive resonance theory. So we implemented a two-layer adaptive resonance theory network with an emotional module, which gives weight to happy and sad outcomes, which means that positive and negative outcomes. So we chose this particular model. Because it overcomes the stability, plasticity, match reset, as well as the search axis concerns. And during every input, there is the winner neuron wins by the equations given over here. And basically, we got good results wherein the performance increased with increase in the emotion weight that was added and the runtime reduced. And we're looking to implement this for mobile robots, autonomous systems, etc. So that concludes my presentation. Thank you so much for the opportunity.
Wonderful. Thank you for joining and good luck with your next phase of your work in robotics. So now the last breakout room. Again, everyone remember that after this is done, this rapid fire, you go to the breakout room to go to the posters that interest you. So now we're going into big data and machine learning. So maybe let's see the first presentation. Okay, great. NeuroTrail, are the speakers there?
Yes, hi. This is Lars Yastaby from MIT Lincoln Laboratory. So this poster is presenting NeuroTrail, which is the neuron tracing and active learning environment for large-scale brain mapping. It's a scalable pipeline with algorithms to automatically generate annotations of neuron structures and then serve for visualization and review by domain experts in a web browser interface. So NeuroTrail is adapted from Google's open source NeuroGlancer, and we've added custom functionality for 3D editing of polygons, line strings, and single point annotations generated by segmentation algorithms, which supports iterative machine learning training. So look forward to discussing more details. Thank you.
Excellent. And again, in this brain initiative, lots of large data. This is great. Okay, the next presentation from nearby, from again, UCSD on modeling regulation of cortisol. Are the speakers there?
Hi, yes. My name is Trisha Satish and I'm from UC San Diego. Our group focused on modeling regulation of cortisol balance for stress resilience and improved mental health. In the face of COVID-19, there was a 31% increase in anxiety or depressive symptoms, with scientists suggesting only continuing deterioration post-pandemic in mental health. The catastrophic stress factors of the pandemic are a trigger for PTSD, a trauma and stressor-related disorder that impacts the physiological reaction to stress via cortisol response. Our team investigated the difference between the cortisol regulation within the hypothalamic pituitary adrenal axis of people with PTSD and those without mental illness. We model a proportional derivative controller, a highly measurable and patient-specific solution to normalize and improve the stress response of those with PTSD. Thank you.
Wonderful. Control theory at work. Next presentation on MRI fingerprinting. So the speaker there from Ethiopia. Welcome. Hello, are you there? Okay, calling once, calling twice, calling third. Okay, look, I
yes,
think.
and please unmute yourself, right?
Hello, Muhammad, are you there on the, I cannot tell. Okay, good, we might come back in case, he shows up. So maybe advance to the next one. So this is about context-free grammar of the RNA sequences. Are you there, speaker, again from Tunisia? Well, the good news is it's all international. The bad news is it's kind of difficult for everything to go so well. Again, we might come back in case the speakers show up. Can you go to the next one? Okay, so there isn't any. And so is there anyone who did not get a chance to present? All right, looks like everybody who is here did get a chance to present. So wonderful. Now, to everyone attending, please, I'm about to open all the speaker rooms. So, at least as far as I can tell, there are at least, 4 rooms and about 3, 5, 8. So it's a good number for you to, okay, I think speaker room is open, somebody who has done it. So great, please go to the speaker room of your interest. Okay, the breakout rooms and interact with the poster presentations.
Thanks, just one technical issue here. If you have an earlier version of Zoom, you may not be able to roam around between breakout rooms. So just make sure that you have updated your Zoom application to the latest version, 5.3 or later, so then you can freely move around between the breakout rooms. And we'll see you back after our extended lunch break. So this will be at noon of Pacific time, 3 p.m. East Coast, and you figure out wherever you're in the world what time it is. So we'll be back in about 50 minutes. So please roam around in the rooms and give some feedback to Professor Thakur, right? Because we'll be handing out some special some awards for student best post presentations.
I would definitely very much welcome that. So please just directly text me. That would be the ideal way to communicate if you found any particular poster, presentation, content and results impressive. So please send me a note. That will be most appreciated. Okay, enjoy the poster viewing.
Okay, well, wonderful. Good afternoon to everybody. We are delighted to have you back again and for the second symposium. Before we start the symposium, I would like to introduce the co-chair of the symposium. I'm honored and pleasure to introduce my distinguished colleagues and friend, Dr. Sridavi Sarma. She is the co-chair with me of this special symposium. And we are going to focus on cognitive neural engineering and natural intelligence. As I indicated at the opening remarks, I think this is the superb extension of the previous workshop, the focusing, moving into the cognitive area and also the natural intelligence. We have 3 exceptional speakers today, and the Giacomo, Indiveri, and from Zurich, he is connecting us, and Holly Jimison, as you all know, and the Paul Sajda. And so we will start with Giacomo, and I'm sure that all of you know him very well. It's a delight to have Professor Indiveri. He's holding joint positions at both the ETH Zurich and also the University of Zurich. As you all know, he significantly contributed to the field of neural informatics, and also he has developed the novel approach to really study real and electronic neural processing systems, and mainly focusing on spike detection learning. And his research and the focus on highly unique, actually, the data acquisition system, recording systems, and he has been honored many awards, and especially I would like to acknowledge the one He was the recipient of the ERC standing grant on neuromorphic processing in early 2011, and also the ERC consultative grant on neuromorphic cognitive agents actually in 2016. And he is a fellow of the European Research Council and also the member of the technical committees of the IEEE circuits and systems. And it's a great honor and pleasure to have you, my dear friend, Giacomo. Floor is yours. And you're going to talk 50 minutes, 45 minutes. We may have a couple minutes, the urgent question, if any. Otherwise, Sridevi and I, we would like to have the questions at the panel discussion section. She and I, we will be leading on this. Okay, you have the floor. Thank you.
Thank you. I hope you see the screen. I hope you see my slide.
I do see.
Yes. Okay. Perfect. Thank you. So thank you so much for the kind introduction. It's really a pleasure to be here and to have the opportunity to tell you about the work that we are doing at the University of Zurich and ETH Zurich on neuromorphic circuits. And I called it neuromorphic intelligence exactly because the topic of this session is really the links between natural and artificial intelligence. And so just to give a quick overview of the difference between artificial intelligence and biological intelligence, we all know that artificial neural networks are basically simulating abstract algorithms using point neurons mainly, or very, very simplified models of neurons that have some weighted inputs and then some nonlinearity. The main feature or characteristic of these algorithms is that they are run on hardware that is completely decoupled from the function. So you can run these neural networks on CPUs, on GPUs, on Intel processors, on ARM processors. It really makes no difference. It's also one of the strengths of these algorithms. On the other hand, biological neural networks are very, very different. As we all know, neurons are really shaped in different ways. The morphology of the neurons really determines the functionality. And these networks, these functional units use the physics of electronic circuits, of their electronics, to emulate real neurons. This is for neuromorphic, but also in biology, these units use physical real time and circuit dynamics to compute through their time evolution. So time here represents itself, unlike in software where time is also completely decoupled from physical time. Also, what is important is that the morphology and the structure of the network determines the functionality. So in biology, the physical hardware substrate is the algorithm. It's really not decoupled, which is a strength and a difficulty, because the strength is that, as we all know, we can do amazing types of computation with extremely low power. The difficulty is that there's really still no formal method of understanding how to synthesize these types of networks to do arbitrary computations. There is not a compiler or a PyTorch toolbox that we can download to understand how to connect neurons to determine the functionality. But these are the main differences between artificial neural networks and biological neural networks. And building hardware that works more close to biology is something that has been proposed already many, many years ago. Just to give you also to show you the strength of artificial neural networks running on GPUs and CPUs, we know now that neural networks can do different types of computation from the 80s, but only since 2009 and 2011, recently, we really started to achieve results that are extremely impressive and that can actually be used in applications, even in the type of applications that we've heard also earlier today. The main reason for this is the fact that hardware became faster and faster thanks to Moore's law, but also that we got access to a very large amount of data. In this case here, you see in the picture, visual type of data, images and movies, but also from this morning's sessions, also biosignals and biological type of data. And this allowed this framework to implement extremely performant architectures. And throughout the years from 2009 on to 2011, there's been many, many improvements by the community in artificial intelligence. There's actually a very nice summary and account of these achievements by Terry Senowski in his 2018 paper. And by the way, if you have access to the PDFs of this presentation, whenever you see things in square brackets, you can click on them and you will get the source of the information. So there is, however, some problems with, as we all know, with artificial intelligence approach. The International Renewable Energy Agency pointed out that if we carry on this trend of just increasing performance by having larger, faster computers and more memory parameters, the ICT industry will start to consume over 20% of the entire world's electricity just to do computation using AI. The main reason for this power consumption is in the fact that these architectures are really using von Neumann type of processing, where memory and computation are separate, and the data movement is really the source of the cost, which is very different from what we do in biology, where the synapse is at the same time the site of memory and the site of computation. In addition to these technological problems and sort of energy consumption problems, we also know that these AI algorithms are quite brittle. So they have some theoretical or algorithmic challenges. They're the so-called narrow AI. These deep networks are programmed to perform only a limited set of tasks, and they operate within a predetermined, predefined range. They're not as flexible or as general purpose as biological neural networks. And even Jeff Hinton, who was one of the main drivers of AI, both in the 80s and also more recently, in an interview, he says that he is deeply suspicious of the backpropagation algorithm, which is the driving force behind this AI revolution. And he doesn't think that this is how the brain works. And he thinks that it's some of the students, maybe someone in the audience, that will be suspicious of what we say, also we here, myself, and question all of these things and maybe explore alternative approaches. The idea is that we are all stuck in a local minimum trying to make incremental changes over backpropagation through time or backpropagation algorithms, and maybe something radically different and disruptive will lead to understand how the brain actually does learning and computation.
Giacomo, I apologize to interrupt. There is a black screen on the top.
Oh, sorry.
If you don't mind turning. Yes, thank you.
Yeah,
didn't want your slides to be obstructed.
Thank you. Thank you for pointing that out. I hope it's better now.
Yes, thank you.
And okay, so there are some algorithmic limitations. There are some technological limitations. What can we do to overcome this? Knowing also the difference between artificial intelligence and biological intelligence. The fact that natural intelligence really can outperform artificial intelligence is known. There is existence proofs. Even if we look at, we don't have to resort to human brains or very, very complicated structures. Even if we look at insects like the bee, we will be amazed at the amount of computation that can be done in such a small volume with such a small weight device that also has many, many less neurons than the number of transistors we can put on chips today, and also with such a huge energy efficiency. So again, remember, the brain, the hardware is the algorithm. This is the main difference between artificial intelligence and natural intelligence. The brain uses time evolution of the physical system to implement its computations. So it's really running through time. Time represents itself. This is also an important distinction between computers and standard artificial intelligence with natural intelligence. And so the neural circuits exploit computation through dynamics, and this dynamics aspect is really important. In addition, we should really point out that these computing elements, the real neurons, are actually very, very slow and noisy, and they are very variable processing elements. They're inhomogeneous. Connectivity is local, and there are very small world networks. Everything is working in parallel with closed loop interaction with the environment. And these devices that we see here can do real-time spatiotemporal processing with always-on learning. So these are really key features of natural intelligence that we should try to exploit if we want to go beyond the limitations of AI as we see it today, despite its huge power and huge performance results. one of the first people that noticed this, that started proposing to use hardware in different ways, not using digital circuits, but analog, and to try to exploit the physics of the circuits to emulate neural function, was Carver Mead in the late 80s, early 90s, together with Mishima Howald. And they were the ones that coined the term actually neuromorphic, and in particular neuromorphic engineering. The approach that was proposed by Carver Mead is what we still follow in Zurich. There are several people that were at Caltech at the time, including myself, Toby Delbrook and Shichi Liu, that are carrying on this sort of framework and this approach of emulating neural function using subthreshold analog circuits, but also asynchronous digital circuits. Around 2008, another community started to use the term neuromorphic to refer to devices, nanoscale devices, these so-called memristors, that because they have conductance changes that are state dependent and are inhomogeneous and maybe even stochastic, they said these are similar to real synapses. And therefore, the term neuromorphic is appropriate also for referring to these types of devices, this type of research. And even more recently, from 2014 on, a larger community of companies, including IBM, Intel, but also research institutions funded, for example, through the Human Brain Project, started to look at spiking neural network chips that maybe are not so disruptive as these analog circuits that Carver Mead was proposed. They were purely digital, or they are purely digital, but that's in any case implement networks of spiking neurons to solve practical applications. So this is the so-called neuromorphic computing community. And so now you see there are all of these communities going from basic research, really fundamental research in academia, to devices and technologies, memory technologies, to more applied research for solving practical problems. And the term here, neuromorphic intelligence, that I have in the title, aims at trying to bridge across all these communities. And if we can really take advantage of all of these properties, going from fundamental research to exploiting new emerging memory technologies and trying to solve practical applications using spiking neural networks, then hopefully we can really go beyond artificial intelligence the way that it is being done now, that is so predominant. And this is the proposal. In the next few slides, I would like to show you examples of how we try to do this, to combine these various communities together and the ideas and the approaches of the various communities, in particular applied to health and wellness. So we've been designing these types of neuromorphic processors that implement spiking neural networks. The idea is, again, to follow the approach of Carver Mead, to use analog subthreshold circuits, which are slow. We slow down circuits to the time constants that are really important for biosignals. So if we want to process biosignals, we have to have matched filters that resonate with those signals. So we have to find out how to slow down silicon to go to milliseconds, not megahertz or terahertz, but really fractions of hertz. By construction, they are massively parallel. Because they're analog, they're imprecise and noisy, but we try to use this as a feature and not as a bug. And in order to overcome the problems that come with imprecision and homogeneity, we have to use adaptation and learning and all of the tricks that biology uses in order to be able to carry out robust computation. And by construction, because of the massive parallelism, all of these architectures are fault tolerant. And through adaptation and learning, they're mismatch insensitive. The fact that we use spikes and that these are all or none events allows us also to use digital circuits, so we can use the best of both worlds. And once we have digital signals, we can use all of the infrastructure that is available from the digital, many years of work that have been done for digital circuits. We use lookup tables, FPGAs, and memory circuits that allow us to reprogram the network connectivity. So we can do feed-forward networks, recurrent networks, convolutional networks, just by programming lookup tables that allow the analog circuits to talk to each other in different ways. And you see, we make custom layouts using both analog and digital circuits together. So I just want to point out that this is not supposed to replace artificial neural network technologies like CPUs and GPUs. There are things in which this type of technology can be useful and things in which it's really not competitive with GPUs. So maybe they can complement it. And the first thing to notice is that these circuits are, even though they are low latency because every single neuron responds as it spikes, and they are low power, they are limited resolution. They're very, very low precise and highly variable. So what are these circuits good for? Well, the title of this conference is really the killer application, cognitive neuroengineering for health and wellness. If you think of it, this type of technology is really ideal for this type of these types of applications, because they can do real-time sensory processing with online and low latency classification features. Of course, these circuits, on the other hand, are not good at number crunching, like going through large amounts of data sets and doing precise derivatives for backpropagation, or even doing bank accounts or putting them on airbag controllers. So this is really not the technology for those types of things. If we do need to do batch processing of data sets, we're still better off using GPUs, TPUs, ANN accelerators, and so on. And then there's the biggest problem of this technology is that, as I was saying before, there is no framework for programming these processors. How do you program a network of spiking neurons to do a specific task? There is still no well-defined framework. The way to do it is just to define a network topology using our own intuition and our own intelligence, to configure the network hyperparameters, which is also very, very difficult. It's a very large dimensional space that one has to explore, and then to implement adaptation and learning. So learning maybe can be used so that in the end you have this black box, but you also need to put on your own intelligence. And maybe one way to overcome all of these problems of not knowing how to configure these spiking neural networks is to understand what are the neural computational primitives that are important. Just like in standard technology, we use logic gates, Boolean logic. Maybe we can find collections of neurons, for example, winner-take-all networks or canonical microcircuits that can be used at a higher level of abstraction. And then we could compose multiple primitives to implement computation, for example, neural state machines or match filters. The question that usually comes is, why do you use spikes? Why do you have to do spiking neural networks when artificial neural networks show that you can do so much with rates, ReLUs, or sigmoid functions? Well, from the point of view of hardware implementations, there is no question. If we have something, we need to process real world sensory data. If the background is really, we want to do online real-time signal processing, for example, to process biosignals. And we need to do robust communication of these signals across long distances. If we have these electrodes, we have wires, we have to communicate through noisy channels. We want to do local processing with these multi-core spiking neural network chips. And of course, we want to minimize power and latency. If we have this background and we have these requirements, just pure engineering optimization techniques tell us that the best communication protocol to use for solving this problem is to use pulse frequency modulation. This has been shown already many, many years ago by Kwabena Boahen and by other colleagues. And by using pulse frequency modulation, it's essentially telling us we need to use spikes. So if we want to process data in hardware locally, for example, with biosignals, just engineering tells us that we have to use spikes if we want to be optimal. In addition, once we decide to use spikes, there's other advantages that can come. And for example, from the Loihi team, Mike Davis, who is the head of the team, in one of his papers in the Intel in 2019 is saying that counter to intuition, computing with spike can be extremely efficient on neuromorphic hardware, even when you could use analog signals, when you could use activity rates. So once you decide to use pulse frequency modulation because you want to be optimal, you get additional advantages just because you have spikes to play with. The other question that often comes is why analog? For example, Loihi is using spikes, but it's fully digital. And analog also brings a lot of overhead and problems to solve. And there are many advantages of using analog circuits. First of all, we avoid using digital clock circuitry, which is extremely complicated and takes up a lot of area. We avoid the overhead of having to convert signals because we want to process analog signals, biosignals. So we don't need to use A to D and D to A converters if we go straight in analog, which can minimize power consumption. But also importantly, if we want to exploit these emerging memory technologies from the memristive community by using analog widths and analog heights of the pulses that are being used to drive these memory cells, we can exploit their multi-level properties, their intrinsic nonlinearities, their stochasticity, and their volatility. For example, if we give a small pulse, a low energy to these memoristic devices that work as memories, they are volatile, they actually forget. And this volatility can be used as a feature and not as a bug. For example, we can use them to implement eligibility traces that last seconds or minutes or even hours. And by using these non-ideal properties of these memoristic devices, we can implement reinforcement learning algorithms in a very efficient way. And this is an example of a paper by Yiğit Demirag just presented last year that shows how to implement eligibility traces using the drift of PCM devices, which is seen as a non-ideality. And again, if you click on these links, you will see that the whole community working on memoristic devices is showing how you can exploit these intrinsic properties to carry out very interesting and powerful computations in neural networks, and in particular in spiky neural networks. So I showed you we can implement these neuromorphic processors. We can actually embrace the non-idealities of memoristic devices to really have dense and efficient and low power devices. What are they useful for? I told you they cannot compete with GPUs if we have large data sets. So health and wellness is like the killer application. And we've been working on this type of pattern classification domain for several years, and we've been looking at zebrafinch classification by looking at the spikes recorded from the zebrafinch to distinguish whether they are their own song or not. We've been connecting our chips to the sensory and the motor areas of rats to implement closed-loop bidirectional brain-machine interfaces. We've been using them to analyze CPGs and to hopefully build intelligent or adaptive central pattern generators. We've been studying ECGs, EMGs, and so on. I don't want to be too extensive. You can, if you're interested in any of these applications, again, you can get the papers. I would just like to focus the last few slides on this very recent application of neuromorphic processors, which is in the high-frequency oscillation detection. So what are high-frequency oscillations? What is this HFO? These are actually spontaneous EEG events in the frequency range between 80 and 500 hertz that consist of at least 4 oscillations that clearly stand out from the baseline. They have been shown to be very useful markers for detecting the epileptogenic zone in patients in which you need to operate to remove the part of the brain that is causing the epileptic seizures. So, for example, this is an example of an HFO here with under the green bar that has been identified by a human expert. And for example, this other oscillation next to it is not an HFO. So it's quite difficult. It's not just simple enough to put a threshold on the energy here and say high oscillations are HFOs and small ones are not, because you really have to distinguish them. If you look at the frequency component of these HFOs, it's quite interesting and it's particular. So here, this is an example of frequency versus time, and you see that some of these oscillations are marked as HFOs, the red ones, and other very similar ones to the naked eye are not HFOs. So again, it's not enough to put a filter and maybe rectification and some amplification part and a threshold. We really need to have a neural network that can be trained to distinguish true HFOs from false HFOs. And this is what we did. We actually created a chip that has all of the components for detecting these HFOs in real time. The chip has a low noise amplifier that can get directly the data from the intracortical EEGs. It has a filter bank, and it has conversion stages that convert the analog signals into spike with adaptive delta modulators. And then it has one of these spiky neural network processors that I mentioned in the first few slides. So we have a spiky neural network in hardware with inhomogeneous and analog subthreshold circuits that can be trained to detect these HFOs. This work was actually done by Mohamed Sharif and Carla Burello, and it was published a few months ago. This is again showing you the pipeline. We basically take the raw signals, the amplifiers and filters that Mohamed designed are then converted into spikes. The spikes are then sent into the on-chip spiking neural network, which uses inhomogeneous neurons. So they're really noisy, they're low resolution, but because they are different from each other, we can exploit the random forest and boosting techniques that the literature has shown to be very effective. So by combining many weak, or I would say crappy classifiers together, we can actually have high accuracy, despite the fact that these are subthreshold, analog, and noisy. Here you see some example of the data. So again, this is a true HFO. When you convert these raw signals into spikes, you get spikes that have high frequency, and then the neurons that receive these inputs with the right weights spike if they have an HFO and don't spike if they don't. So just by looking at the average activity of this population of neurons, you can detect whether that particular electrode is measuring HFOs or not. And then the surgeon can have an extra source of information to decide whether to resect that part of the brain or not. So now we have a standalone sensor and processor that is not being trained with backpropagation. We really use random forest, and then finding the hyperparameters by hand allowed us to obtain a system that could perform the classification correctly. We're using 1-bit weights. It's very low resolution. The one thing that made the difference is the fact that our circuits have dynamics which are slow, in which the time constants of the silicon neurons are matched to the time constants of the HFOs. And the power consumption of the whole system is less than 1 milliwatt. So we can really put this directly on the skull and listen to the spikes and detect whether we have HFOs or not in real time in the operating room while the surgeon is operating. The accuracy is not beating like MNIST 99.9%, it's only 78%. But again, you should think of this as an aid to the surgeon. The surgeon in the end is the one that makes the final decision. And of course, it's also very nice because if you compare it to the state of the art that was published before using GPUs and CPUs offline, it was still lower. It was 67%. So even though we don't have 90%, we still improved over the software state of the art. And we have an online chip that can do this HFO detection. So this is just to give you an example that you don't need to have deep networks with backpropagation to solve complex problems. You can actually do in the wearable and health application domain something interesting with analog subthreshold spiking neural networks with this neuromorphic approach that is combining everything that was going on from Caltech to the latest in memory computing approaches with memristors. In the end, the overall research approach that we follow is the one of mind, brain, and body. It's very similar to the title of this whole conference, Brain, Mind, and Body, but we start actually from theoretical models that have hypotheses on what's going on in the mind. We implement in hardware these spiking silicon neurons. We put them on actuated system and sensory systems. So in the case of HFO, we just have sensors. But in other examples, we actually have also motors. And then through this loop, we refine and improve our ideas of how the mind works, how the brain implements those algorithms, and then how we can hopefully have emergent cognitive abilities or emergent behaviors that are representing intelligence in these closed loop online sensory processing systems. So with this, I would like to just thank the whole group. I'm very fortunate to have a very nice group of very bright PhD students. As I said, Carla and Mohammed have been working on the HFO work, but the rest of the students have also been doing amazing work in other domains. Those list of papers that I showed you. The group leaders, Elisa Donati, Melika Pavan, and Charlotte Frankel are really driving most of the research, and I'm only sort of nudging them. And also our collaborators are really helpful with our work. And also I would like to thank the funding organizations, but mainly I would like to thank you for your attention.
This is wonderful, highly inspiring for Giacomo. We appreciate all this. Any questions? If you have any questions, you can send it via the chat box, please.
Natalie, we can't hear you. Your volume is.
Cannot hear me?
Will we ask a question or do we
if you have, since you're welcome to direct ask question, we can start with Nitish. Nitish, go ahead.
Yeah, so Giacomo, fantastic overview. So with IBM made a big effort. Intel now has Lohi, all of that, and it was still not cracking the commercialization of the neuromorphic computing. And do you want to kind of convey why, the conventional von Neumann has moved forward and neuromorphic has not commercialized so well?
Yes, in fact, I tried to hint at this with saying what is the bottleneck. First of all, IBM and Intel, they're proposing this as a research platform to explore if there are any possible application with these higher power devices and systems. They are really trying to see if things can be scaled up at the cost of more power consumption. Whereas the approach that is more close to the Caltech approach is really doing edge computing. If you need to process sensory data directly on the sensor without connecting to the cloud, then you have this small scale but low power with analog circuits, intelligent or sensory processing devices. So even though Intel and IBM call their devices neuromorphic and I call my systems neuromorphic, there is a big difference there. And of course, they both try to do interesting things, but they're not exactly the same. The other thing is the main reason why neuromorphic has been going on since the 90s, and still, as you say, it's not being adopted by many companies yet, is because we don't know how to combine these neurons. If I can give you 1 million neurons, IBM has given us 1 million neurons, but still we don't know the theory of how to combine these to do intelligent processing. And we can, if we have a specific problem like HFO detection, we can put our own intelligence and create a network that does it. If we have, for example, step counting or measuring if the food has gone bad in the refrigerator by doing olfactory processing, we can do that by just investing 1 or 2 years of research. But there is not a compiler that allows a company to just sell a product on the large market and then adapt it to every single problem. It's really this fragmented market in which many startups will become the leaders in their niche, whether it's olfactory processing or health. But I don't think there's going to be like an IBM or an Intel company that can solve all of the problems in the edge domain with a general purpose solution. Just like insects and animals are very, very specialized to survive in their particular environment, this neuromorphic approach is going to be very, very specialized, and it will require different solutions and different approaches for the different problems. And that's why I think it's still, there's no big company like Samsung, IBM that has the golden solution for all of these problems.
Okay. There's one question from chat box I'm looking for. Is the design chip available? That's the question.
Yes, again, this is work in progress. We always do chips and we refine them, as Gert knows as well. The various groups around the world, there's maybe a dozen, have their own chips. They do give it to collaborators. We are very happy to collaborate with colleagues. Some like Spinnaker are actually making it available on a bit larger scale, maybe tens or hundreds of colleagues. We have maybe 40, 50 of these chips, and if there is interest, just reach out to us and we will be happy to send you one, provided we know that it's going to be used. Otherwise, we only have a limited number, and it's very difficult to give them to a large number of colleagues. But we are very happy to collaborate with anyone interested in exploring these technologies.
Okay. Another question from platform party or from any via the chat box? I don't see any.
I think Gert has his hands up.
Okay,
Gert?
who was Gert? Okay, go ahead, please.
Yes, so Giacomo, very nice presentation, as always. So you showed, you're making an argument that rate coding is a good thing to do for in the spike-based networks, but clearly spike timing is also equally important, right? And in fact, there's a hot debate. We can spend an entire hour with neuroscientists discussing: is it rate code? Is it time temporal code, right? And I guess is both, right? But so question for you is that neuromorphic engineering and spike-based neuromorphic systems in particular have a great opportunity to interface directly with the brain because they speak the same language as the brain, right? You can stimulate, well, you can definitely record spikes and have the spikes go into your neural network, but also you can take the spikes coming out of your neural network and then drive, say, go through electrodes, basically do stimulation based on the precise timing at which you activate the brain. So what you see is an opportunity for neuromorphic neural interfaces, right? That can really then extend all this neuromorphic work with bridging with the neural interfaces community.
Absolutely, it's exactly what I was also trying to emphasize, is the fact that we have these dynamics, and that the dynamics can be matched to the ones of the real neurons. We can really have a dialogue, an interplay between real neurons and silicon neurons. In addition, these silicon neurons are burning a few picojoules. So if you can really put them on the dura and under the dura on the skull without risking of burning the tissue that they are connected to, because if you did it with any digital circuits, well, it would just heat up too much and it would just damage the tissue. So we have also the advantage of low power. But the biggest advantage is, as you say, is the fact that we have the circuits that speak the same language of neurons. We did try to do examples of this where we connected some cultured neurons through a culture to the chip, and then two memristors, and we showed how we could actually create this dialogue between neurons, which actually were in Padova through the internet, because of this was pre-COVID, but still because it was more convenient for the various labs. The signals, the spikes, would go through the internet to Zurich, and then the Zurich silicon neurons would go to Southampton, which then would send things back to Padova. So it was a biosilicon interface through the internet. But we did show that it is possible to have this dialogue and orchestrate the activity of the silicon neurons and the real neurons together, because we slow down them to these 50 or 100 millisecond time constants.
In fact, talking about the delays, and so once you go over the internet, easily you have tens, if not hundreds of milliseconds of delays, and in the brain too, right? So what do you see as the role of delay, as a nuisance or as an opportunity, right, in neuromorphic design?
I think it's a great opportunity. I mean, we in computational neuroscience, we're still now trying to understand what is the golden rule for spike-based learning, and how do you do spatio-temporal pattern processing or recognition like HFOs, but like, if you want to do motor control, if you want to do touch, many of you are dealing with these problems. And in order to do spiking neural networks that can recognize or control or produce the right dynamics, the delays are one of the crucial elements. So it's not only changing the weights, but it's really having a suite of delay elements, like different types of synapses, but maybe even different types of axonal delays that would allow us to increase the computational power of these networks, and then either do the recognition or produce the sequences that are necessary for motor control. I think, and in our chips, honestly, we have not implemented these delays so far, but I think that's a key element that really is needed to make a step forward.
Okay. Nitish, you raise your hand again. Please go ahead.
So, Giacomo, you mentioned Misha Mahwal's name, and in fact, that Mahwal Prize this year went to the EPFL group that in the neuron paper showed that spiking neural stimulation given to the nerves improves sensory perception. So that's a good example of neuromorphic spiking activity interface to the nervous system.
Yes.
So this is very, very, very recent news,
Yes, exactly. Just a week ago.
Okay. Any other questions? I don't see any. Siri, do you see any question from chat? No. There's one more. Okay. What aspects of spike are important? Frequency, amplitude, shape? Can you just count the edges?
That's a very good question. There is actually a large community, mainly in Japan, that argues that the shape of the spikes are actually important and play a computational role. So far, in many software simulations, but also in our chips, we have assumed that a spike is an all or none event. So we have not explored yet the computational abilities or the properties of having different shapes. But it is something which is arguable. So for convenience, now we're trying to see how far can we go just by assuming that a spike is an all or none event. It's just a digital pulse. But it's true that especially from the math theory point of view, you can actually exploit the fact that different neurons have different shapes to carry out different types of computation. In our chips, just to summarize, we assume that spikes are digital. We look at the timing, like Gert said, it's important to look at correlations and maybe coincidence, but also in some applications, it's enough to look at the average frequency, average firing rate, either averaged across populations for having low latency or averaged across time to just improve precision, given that these neurons are noisy.
Okay. Well, this is, I don't see any other questions.
Sorry, if I may follow up.
Okay, go ahead.
This is a really important point made by, right? So in spike-based representations, there's also learning that is based on spike timing, right? And so there's been the consensus or perhaps an axiom in the neuromorphic community that it's all about spike timing, and learning has to be based on relative differences between spike times, right? So do you think, and the assumption also made is that backpropagation is not biological, right? But in fact, Bipu has shown that actually some backpropagation actually takes place through this backtraveling exponentials, etc. Right? So what is your take on biological versus artificial learning rules, and whether there is any common ground, or is it totally disjoint?
That's also like a very, very hot topic. And if you look at the latest NIPS or NeurIPS papers, there seems to be now a lot of interest from the computational, machine learning community to find local learning rules. I don't know why, but there's this trend to go towards neuroscience from the machine learning, and it's very nice to see that there is a convergence. So there are many attempts to show how to implement backpropagation with local learning and with biologically plausible learning rules, going back from feedback alignment to surrogate gradients now to these latest papers that are appearing in these very days in the NeurIPS proceedings. I agree completely. So the spike timing is important, and from these papers, but also from computational neuroscience, from our colleagues that have been studying these things also for many years, it's clear now that it's not only the timing, but you need to look at other state variables in order to really implement powerful learning rules, such as the membrane potential, or maybe a proxy for the calcium concentration, either at the synapse or at the soma, or both. These would be also considered as eligibility traces. And maybe the latest thing is these at the network level with feedback alignment type of signals, that these are the ones that are appearing in NeurIPS. It's possible really to approximate backpropagation by using not just a single neuron, but either dendritic compartments or multiple neurons. That was the thing I was trying to find out, is dendritic compartments seem to be now the latest trend in trying to see if you can implement learning rules, spiking neurons that approximate backpropagation.
This is highly inspiring and very talk, and also very fruitful discussions. We appreciate for this, and I would like to give the floor to my dear friend Siri. You have it. Thank you so much.
Excellent.
Thank you. It was a pleasure.
Excellent. Well, yeah, so I guess we're in for another treat. So I'm honored to introduce Dr. Holly Jimison. She received her BS in mathematics at the University of Illinois and her PhD in medical information sciences at Stanford. She's currently a joint professor in the Curry College of Computer Sciences and the Bouvet College of Health Sciences at Northeastern University. As a fellow of the American College of Medical Informatics, Dr. Jimison has made significant contributions to the field of biomedical informatics in the areas of pattern recognition, decision support, and consumer health informatics. So she continues to deepen her influence in the field through her research on technology for successful aging and scalable remote care for the elderly, including models for tailoring interventions in cognitive exercise, physical exercise, socialization, and sleep management using new behavioral metrics derived from this type of data. As I was kind of doing a little exploration, Dr. Jimison, I found out, is actually also commercializing. She's built a platform. It's called New Coach, if I'm pronouncing that correctly. It's a modular health coaching and research platform supported by mobile health technologies. And it's being commercialized by, I believe, her company called NovoWell. And they're developing this platform. The New Coach platform allows researchers to gather vast amounts of data from participants in real world context in near real time. And then this information can be used to learn more about a person's behavior and provide just-in-time feedback and motivation for achieving health goals. So I thought that was really exciting. So today, however, she's going to tell us about from brain to behaviors, unobtrusive measures of cognitive function. So welcome. Thank you for joining us.
Great, thank you so much. I'm really happy to be here and talk about how we can extract information on an individual's cognitive abilities just from looking at behaviors. As she was saying, most of my work is about delivering health interventions to the home, coaching how to change health behaviors. But a large part of that that's really necessary is understanding the cognitive function and the abilities of people. Because as we look to modeling cognitive performance using these home monitoring data, it's a new approach to managing neurological conditions, to looking at the benefits and effects of cognitive interventions, as well as recovery and rehabilitation efforts. For example, stroke or traumatic brain injury. And finally, early detection of cognitive decline is growing interest in this area. And the types of data sources that are truly unobtrusive are like motion sensors in the home, computer interactions, typing speed, mouse movement, phone sensors, and then I'll describe some metrics that we've embedded within adaptive computer games. And the important benefits of this type of approach is that we have